Well, today we're going to move on to fluid bed technology. And then we start with the mills and the mixers. Mills are really simple. 2 VFDs, 2 motors. That's a mill. We moved on to mixers. Now we have 2 motors. We have valves. We have a little more. Well, now we're going to move on to a much more complicated device. We're going to move on to the fluid bed. And inside the fluid bed, we have the potential of 3 types of processing. We can do fluid bed drying. That's where you take the product from the wet mixer. Oh, we need one more chair, gentlemen. Coral's here, yay! Coral, someone stole your chair.
Where's my chair?
I just tell you, someone. Oh, there you go. There's an extra chair right there. So inside the fluid bed, we can do drying. Drying is where you take the wet material out of the mixer or out of the wet mill, move it to the fluid bed, and dry it. Remember I said yesterday, that's the challenge. If you put 30% moisture into your mixer, you now got to take all that moisture back out inside the fluid bed. So fluid bed drying is basically is simply the removing of water or liquid, a solvent, using a carrier gas. Now inside fluid beds, for today we're going to talk basically about using air to fluidize the product and dry it. We have quite a few customers that use nitrogen to dry their product. But we're not going to talk too much about those guys today. We're going to focus mostly on just air. Inside the fluid bed, you can also do granulation. So just like a high shear granulator, a mixer, you're taking a fine powder, adding liquid, making a more dense granule. You can do the same thing inside of a fluid bed. It's called top spray granulation. Top spray granulation will spray onto a product, let the products collide with each other, make bigger products. And the third process inside of a fluid bed is Worcester coating. Worcester coating is where you take a particle, either a powder, a bead, a tablet, a mini tab, and you take the individual particle and you coat just the individual particle. That's Worcester coating. So those are the 3 types of processing we can do inside of a fluid bed. Fluid air, for those who don't know, manufactures equipment all the way from 2 liters up through 1,200 liters. The statement here about a 500 gram insert, we no longer make. I'll tell you the reason for that in a few minutes. Obviously we can process using air or nitrogen, and then we can do solvent recovery or solvent destruction. A lot of pharmaceuticals actually manufacture their product using methanol, isopropyl alcohol, methylene chlorides, a lot of solvents. Some states, some countries require you to recover the solvent. Others will let you destroy the solvent as it leaves the machine. So we'll talk a little bit about solvent usage. So a quick slide on our fluid beds. The one in the left-hand side, there's a Model 2, similar to the one in your lab that Tony sold on us. Right?
Sorry.
You sold the Model 2 from the lab, right?
Yeah.
The lab no longer has a machine.
Almost.
Coral has no job now. What are you going to do, Coral?
It's almost so, sir.
Coral, what are you going to do? What are you going to do without a fluid bed? So that's the Model 2. The Model 2 can do Worcester coating, top spray granulation, and drying. And then we manufacture machines all the way up to pilot scale portable Model 50s. We can then do production machines all the way up to 1,200 liters. We can do bottom dump machines like Pfizer's, a couple different things as well. So looking at the process train, if you will, as far as the product line, Model 2, Model 5, there's a Model 10 in there, Model 20, Model 50, all portable, all go through a doorway. After the Model 50, you start going to Model 120, 120 liter machine, Model 300. The model numbers refer to liter size, by the way. All the way up to 1200s. On the R&D side, again, the Model 5s, that's actually our friends at, that's Whooshy's machine there. That's a 5-liter portable, 20-liter, 50-liter portables. The neat thing about the 20s and 50-liter portables that make us unique to anybody in the industry is we make a 50-liter portable. Vector's 50-liter is a fixed size machine, which means you have to dedicate a room for it. You have to do all the construction work to put it in the room. Our Model 50 and our Model 20, the entire head of the machine opens up, folds over, so that this can fit through a standard doorway. Just like our mixers, that means the customer no longer has to dedicate a room to a machine. More importantly is there's no construction costs. I can literally roll that machine into a room, plug it in, and start manufacturing the day it comes out of the skid. In fact, at Farmaron, the first machine they took delivery of last October, we rolled it off the skid, turned it on the very same day, started IOQ a day later. That's huge for a customer who needs to get moving very quickly. It saves them all the construction costs. The construction costs for putting a normal machine in can be as much as $100,000. So you save them $100,000. And that's a huge one when we go to sell. When we start comparing ours, if we come across a vendor, competition, selling a fixed Model 50 against our portable Model 50, it should be a win for us every day of the week. We might be more upfront, 0 construction costs. Our machine arrives fully validated. All the loops are tuned. He can start the IOQ the next day. Your fixed machine can't do that. Now, unfortunately, these slides here are the old Model 2. This was the old Model 2. It sat on the bench top, looked like a coffee maker. The new Model 2, is this one here. The old Model 2 has some deficiencies. The chamber really wasn't tall enough for processing. It had no PLC controls on it. It was less expensive, which made it easier to sell, but it didn't quite process as well as you would have liked. The slide here on the right is the we call it a mini processor. It would actually let us run down to 3 to 10 grams of product. The reason we stopped manufacturing it, you could never make it work consistently. And anybody who tells you Glot makes a mini processor, yes. Vector does, Gia does. I can make them work for one batch. If I run the exact same batch, the exact same way tomorrow, there's no guarantee it'll work. The reason for that, as I mentioned yesterday, sunlight hitting the machine would change the way it manufactured. The HVAC in the room would affect how it processed. If Coral put her hand on the machine, and today her hand was very warm, it would affect the way it processed. That's how temperamental it was. So, although customers keep asking for a mini processor, the fact of the matter is I can't reliably sell them something that will not work every day the same way. So we stopped manufacturing it. So sales, you get the request, well, can you make a 10 gram machine? Sure we can. Yeah. We won't, and here's why. We won't make it, because I'm going to tell you, Mr. Customer, it will never work the same every day. Not because of the machine, but because of the simple effects of thermodynamics in the room. We don't want to do that to a customer. Sell them something for $100,000 that's not going to work. That's just not good business. On the large scale machines, we go all the way up to, here's an 800 liter. We've got a 12 or 1,000 liter now sitting up at Pfizer. We've done a 1,200 liter. Scalability. I start with this slide normally so everyone's thinking about what works in a fluid bed or how a fluid bed works. So, actually I'm going to skip that slide for now just because I'm going to go back up for those who don't understand fluid bed. Has everybody in here run a fluid bed before? You've obviously run one now. You've run a fluid bed. Coral's run them. Tony and Thomas has. I know Frank has. Okay. So basically in a fluid bed, what you're going to do is you're going to put product inside the bowl. This is the bowl. You're going to suck air through an air handler, through the product. That's going to cause the product to raise up inside the chamber. The product's going to bounce around, suspended in an airstream. Once that particle is suspended in an airstream, I can dry all of it at once, of each particle. The air is going to leave, go out the fan, and out the building. Sounds kind of simple. Inside the air handler, we're going to control the humidity. We're going to control the temperature. We're going to control the amount of airflow. We're going to control a couple other parameters, and then the air is going to leave. That's the basics of fluid bed drying. Take the particle, get it up in the air, bouncing around, and then process it. There's two types of fluid beds that we're going to talk about. No bypass and with a bypass. So now we're talking no bypass. All of the air is going through the air handler, through the product, through the fan. There's no bypass air. Worth noting, every fluid bed Fluid Air has ever manufactured is going to have a fan on the outlet. We will never put a fan on the inlet of a fluid bed. A couple of reasons for that. By putting the fan on the outlet, my chamber is always under vacuum. That keeps the product inside the chamber. The other important thing is the chamber is running in a vacuum. Should there be an explosion, remember we talked about yesterday, dust, oxygen, all you need is a spark and you've got an explosion. By keeping the chamber negative in a vacuum, I can now measure a positive pressure. If the chamber goes positive, there's only one way for it to go positive. There's been a deflagration. There's been an explosion. Both the same thing, deflagration, explosion, same word, same meaning. We try to use deflagration in our industry not to scare customers. Explosions scare customers. So on a fluid bed, okay, where's my mouse again? There we go. You're going to fail the test.
Sorry, sir.
Are you going to sell a machine?
Yeah. Tell more.
Is that a sales meeting?
And there's a training on there.
Oh, their training's more important than me.
No.
You hear this, guys. When Tony calls me next week and says, I really, really need you in Beijing. No. It's okay, I'm just giving you a hard time. I understand. Lena left me too. I understand. So, as the air goes through the air handler, so the fan's going to suck the air. The air is going to get sucked through the air handler. The air handler is going to process it and condition the air. So that could be dehumidifying it to make it drier. It could be heating the air. It could be, there you go, humidifying the air. Why would you humidify the air? Well, we're going to talk about that in coating, but if your air is too dry, it can affect your process in a negative way as well. We're going to chill the air to keep the dew point low so we have dry air. We're going to heat it using steam coils. Now the picture says steam coils. On portable machines, it's electric heating. It's electric heating, not steam. We're going to use a series of butterfly valves to control the machine's airflow. The air is going to come in to the plenum. The plenum is the section underneath the bowl. So in this case, the air is coming in. It's got to come in, turn 90 degrees, and go through the machine. So inside the bowl, we put a filter plate. That filter plate creates pressure drop. That pressure drop forces the air to be evenly distributed across the plate. The air is going to go through the expansion chamber, through the product bulb into the expansion chamber. Inside the expansion chamber, we can have various filters. The filters are there to keep the air, keep the product in the fluid bed, allowing the air to leave. We can do a one-piece filter bag. We can do filter cartridges only. We can do a combination of both filter cartridges and filter bags. And a little bit later, we'll go into the reason as to why you have such a variety of filters. Obviously, sensors. We're going to need to measure the dew point to control it. We need to measure the inlet temperature so we can control it. Product temperature, outlet temperature, airflow, pressure, vacuum. So there's numerous sensors that go into a fluid bed. Ask Diet, I think he's wired every one of them now. Diet is now the expert. And then the process blower. Process blower, we're going to talk two different ways today. Up until about 7 years ago, the process blower in the fluid bed was always running at the same speed. We ran it at full speed, and then we used a valve on the outlet to control the airflow. About 7 years ago, we decided to start switching over to VFD control. It was a green initiative, so in order to save electrical power, we switched over to VFD controls on our blower. So the good news is, on our new machines, we use a VFD. The bad news is, from support side, whoever we supporting equipment, like the old Pfizer 500, uses a valve on the outlet to control airflow. So don't be surprised if you can't find a VFD on an old machine. So general concept of fluid bed use. Make sense? Coral knows it by heart. She's been running it for a couple of years now. I liken it to a hot air popcorn popper. Once you get the product moving, you can heat it, you can spray onto it, you can do everything you want inside the fluid bed.
Yeah.
So
Yes, go ahead.
After the blower, the valves, is it using for the controlling the airflow? Or?
Right. On the machines with a valve here, what you would do is vary the valve's position. As you vary the valve's position, you change the pressure drop. As you change, remember your fan curves, as you increase the pressure drop by closing the valve, the airflow falls off the curve. As you want more airflow, you'd open the valve up and you'd move this way on the curve. It was a very clean, simple, efficient control. VFDs up until about 10 years ago were very expensive. So if you had to put a VFD, a variable frequency drive, on a large blower, 100 horsepower, 200 horsepower blower, the VFD could cost you $30,000, $40,000. That's kind of expensive. The valve cost me about $500.
Yeah.
So we did it. Up until about 10 years ago, most pharmaceutical companies did not care about the environment. The green initiative, saving power, conserving utilities, believe me, nobody in pharmaceutical cared about that 10 years ago. The drug was so expensive they didn't care about the environment. They're finally starting worldwide to become more cognizant of the green initiative. So customers started asking us, can you save us electrical power? Can you lower my energy costs?
Yeah.
Fortunately, VFDs came down in price as well, which is good. A $40,000 VFD would be a tough one to ever recover the cost on. So that's why we made this change about 7 years ago. Is when we finally agreed to do everything using a VFD on the blower.
So once we are using the VFD, the valve is not.
The valve goes, well, the valve for control goes away. You still might have a valve here
Yeah, that is.
to block off the
Right.
chamber,
Okay.
but there's no longer a valve to control
Yes.
airflow.
Okay.
I have one question.
Yes.
Can you explain why we measure dew point, not humidity?
Absolutely. Hold that thought till we talk about the air handler.
Okay.
Okay, we're going to talk about the air handler in a few minutes, but that's a good point. We do not control humidity. Any vendor or any customer who tells you they want you to control RH, relative humidity, doesn't know what they're doing. And we're going to talk about why that is in a few minutes. From a sales standpoint, you love it. If you hear a customer tell you that vendor A just quoted them a machine and they're going to use RH. RH is cheaper to control, cheaper to censor. But it will not give them consistent control. So now you are the expert, and you sit up and say, well, Mr. Customer, yes, I can sell you an RH sensor, but you're never going to get the same product quality, and here's why. And now you're the expert saving them, and you make the other vendor look stupid. And we're going to talk about why in just a few minutes. So we're going to look at the fluid bed, and we're going to basically walk through a fluid bed from air handler to chamber to blower to sensors. And then we're going to talk about processing inside one. So it's a lot of material. The neat thing is everything we talk about for a dryer gets used for top spray granulation. So everything's going to, remember I told you yesterday, everything we do today is going to build on it. So slide 1 is going to build to slide 10. So a lot of information to remember. Standard fluid bed here. This is actually the one, this used to be at my facility. We used to have a manufacturing facility. So the air, there's a pipe in the back, the air is coming into the plenum. The plenum is this area here. The air is going to come in, turn, go through a distribution plate, through the bowl, and into the process chamber. Neat thing about fluid air, we use one chamber for everything. Drying, top spray granulation, Worcester coating, one chamber, one bowl. Your competition, and they all copy each other, they all copy Glock, uses a different chamber for drying, a different chamber for top spray, a different chamber for coating. So what they do is they have a chamber that swings open and closed. It's actually a neat design. 30 years ago, it might have been the best way of doing things. Nowadays, it's got a lot of deficiencies. Imagine, if you will, having to buy 3 chambers. And I'll show you a picture of a lot later today. Imagine having to buy 3 chambers and swing one out and swing one in depending on your operation. Wait, you can only have one on swinging in and one in the machine. What do you do with the third one? The third one had to sit in a storage unit. You had to raise it up and install it on the machine. Very large stainless steel pieces being hung over your head. In fact, South Carolina 3 years ago had an operator just about killed by one where it fell off and hit him. So, unique to fluid air, one chamber. We've designed our chamber, done the FEA, finite element analysis, done the solid modeling through spray systems to use one chamber to achieve optimal performance in both dry, granulation, and coating. That's a big difference on our chamber. Again, standard diagrams. This one I've actually added and shown. Usually we put a filter housing on the outlet of the machine. No filter bag is 100% efficient. Some powder will get through. You don't want to dump product to the atmosphere. You don't want drug blowing into the high school next door. So we put a HEPA filter on the outlet of the machine. Any powder going through the fluid bed gets captured so it doesn't end up in the environment. Again, this picture shows the airflow valve out here. That's from 7 years ago. Nowadays it's all VFD. Remember I said, standard machine, all the air goes through the air handler, through the product, through the blower. That's a non-bypass machine. Well, what's a bypass machine? In a bypass machine, some of the air, all of the air will go through the air handler, some of the air will go through the product, some of the air will bypass the chamber, all of the air will go out the blower. Why would you do that? Any ideas? I'll give you a hint. By doing it this method, we can actually gain a larger range of airflow. So let's go ahead and look. Oops. So in this case, all of the air has to go through the air handler. What if I want to run a very small product load? I want to run instead of running a 500 liter batch, I want to run a 100 liter batch. Well, a 100 liter batch needs a lot less airflow. Well, the fan's on a VFD. I can turn that fan down to a very small airflow. The problem is at small airflow, all of your control at the air handler becomes inefficient. Air handlers like to run at a certain amount of air going across it. So as you lower the airflow to achieve what you want here, you lose all your control here. So with the bypass, I can still bring a lot of air across the air handler, achieve very good, very efficient temperature control, very good, very efficient dew point control. But then instead of putting all of the air through the fluid bed, I can say give me 100 through the fluid bed, 900 through the bypass. And now I can run small batches. That's the other advantage in our fluid beds. Most of your competitor fluid beds won't let you run very large and very small batches in the same machine. We call it turn down ratio. I'll show pictures a little later. We run a model 300, which is 3 coating columns. Inside the same machine, I can run 1 coating column. I have a 500-liter coating machine with 7 coating columns, and I can put a 1 coating column bowl in it because of the turn down, allowing the customer to basically get 2 machines for the price of 1. That's very unique to Fluid Air. It's a little more costly, but instead of buying 2 fluid beds, a 1 coating column model 100 and a 7-tube model 500, the customer can buy a bypass machine and get 2 bowls, and he gets 2 fluid beds. 1 chamber, 1 air handler, 1 fan, 1 piping. 2 bowls, he gets 2 machines.
Yeah. Sir.
Yes, sir.
Question. If I want to reduce the airflow which goes into the chamber,
Yes?
which valve should I open or close?
Sure.
The bypass valve or the
We actually do both.
both?
What we end up doing is, how to explain this safely? In order to control the airflow down low,
Yes.
what you want to do is balance the pressure drops.
Yes.
So what we do is these 2 valves are actually connected together.
Yeah.
As one opens, the other closes.
Yes.
So the control systems, all you tell us control systems, I want 100 meters cubed per hour in the chamber. The control system automatically closes this valve and opens this one until it achieves your 100 meters cubed per hour.
Okay.
Because again, if the air is going to want to go through the bypass because there's nothing stopping it. There's product here that's going to stop the air. So what you do is put the 2 valves together, you balance the pressure drop, and you get the air flowing freely through both sides. Now, from an engineering standpoint, there's a whole lot of work here. This pipe is actually a different size pipe than this pipe. The CVs, coefficient of velocity, volumetric coefficients, on the valves have to be set. So a lot of engineering work, but basically all you're doing is adjusting these valves automatically to control the amount of air through here.
Yes.
Okay, air handlers. Air handler, air handler, air handler. 2 things really affect the performance inside of a machine, the air handler and the fan. The air handler is going to control your dew point, your temperature, your air filtration. Fluid Air offers 3 types of air handlers. We can do a horizontal air handler, a vertical, we can do splits, we can do stacked. Horizontal air handler, we've been talking about it all day. Here's a horizontal air handler. We can do a vertical. So literally the air comes down and then into the fluid bed. We can make a U. So imagine the air coming in and then turning. This way you can fit the air handler in a smaller space. We can actually separate parts of the air handler. We can have the humidification grid up here, piped over to the temperature grid, piped over to filters, and then to the fluid bed. So we can customize the air handler to fit the location of the room. That's also important for customers who are trying to put machines into existing buildings. The air handler is probably the biggest piece of mechanical equipment. So in order to make it work, we can split it up, stack it vertically, stack it horizontal to save them space. Now, obviously the cheapest one is a horizontal, which this one shows here. On a standard air handler, you're going to have roughing filters and a bird screen. The roughing filters keep out big particulate. It then goes through a preheat coil, a humidification grid, dehumidification grid, temperature section, air blending, HEPA filtration. All inside that little box is all that control. Now why do we have all that control? A couple of reasons. Obviously temperature is pretty simple. The hotter your air is, the faster you can dry product, as long as you don't burn your product. But why would you ever want humidification and dehumidification in the same machine? Picture Beijing in August and Beijing in January.
Oh yeah.
The outside air changes. So if you use the outside air by itself, In the summer, you dehumidify the air, you have a drying time of 45 minutes. In the wintertime, the air outside is more dry than your dehumidification. It's got a lower dew point. Now your drying time is having 45 minutes, is 35 minutes. It's not bad, you dry faster, but you're no longer consistent. That becomes very important when you start talking dew points for coating. Preheat. The reason we do preheat, 2 reasons. It's something that's an option. You offer preheat in areas that have freezing air. The machine is turned off for 2 weeks. You've got sub-zero weather outside. That cold air going across your steam coil can freeze the coil. It's got water in it. Water expands when it freezes. It'll damage the coil. So one reason for preheat is freeze protection. The other reason for preheat, if you're doing humidity control, you have to have preheat. Cold air, you cannot add water to cold air. To add water to air, you have to heat it to a certain minimum. So the preheat allows me to warm the air so it'll take humidity, take moisture. The preheat section on the machine, the reason it works for freeze protection, no electrics, no pneumatics, no nothing. It controls itself via expanding gases. So that's why it works for freeze protection. I can turn the machine off, turn off all the utilities, go home for 2 weeks, and not worry about it. The valve will automatically self-regulate based on the expansion of a gas. Inside the air handler, I haven't forgotten your question yet, so I haven't forgot yet. Inside the air handler, here's what it looks like. So you've got on the inlet a series of pre-filters to take, more or less scrub the air clean. Not super efficient, just get all the big particulates out of it. The humidification grid is really just a series of pipes with small nozzles in them. Spray nozzles. The spray nozzles turn the water, clean steam now, not water. You're taking clean steam, so you're taking DI water, boiling it, turning it to steam, misting that steam in through these nozzles. The air comes across it, absorbs the moisture, raises my dew point. The air then goes across a coil. This coil has cold water in it. Most plants have chilled water. We run the air across a chilled water coil that dehumidifies the air to get to my final dew point. The air then goes across, these are a series of valves. So these valves here are all closed. These valves down here, 2 valves in here, are open. They're linked together. As one opens, the other closes. That adjusts how much air goes across the heating section, the face, how much air bypasses the heating section, face and bypass. That allows me to adjust the amount of temperature I'm getting to the machine. Now this is for a steam heated machine, non-portable. Remember, portable machines do not have steam. They use electrics. So on the electric ones, we vary the voltage across a resistor to change the heat. Much simpler on a portable machine. The air then leaves the face and bypass section. We have an air blending station and a HEPA filtration. The HEPA filtration is what we were talking about this morning. Our friends at Pfizer screwed up for the last 2 weeks, and we finally got fixed last night. Talked about preheat control. Preheat uses a capillary control valve. So picture a valve connected to a steam pipe. The other end of the valve goes to a sensor bulb full of gas. As that gas gets warm, it expands. The expanding gas closes the valve. When the gas gets cold, it condenses, it opens the valve. So preheat works with no electrical and with no compressed air. It's basically expansion of the gas inside the sensor opens and closes the valve to maintain preheat temperature. That's how I get preheat control without utility power. Oops, I skipped it. There we go. Skipped ahead a little bit. Humidification control. We talked about it. We use clean steam. We inject clean steam into a series of nozzles to humidify the air. We talked about dehumidification control. Now here's where we're going to talk about what you control. Dew point. RH, if you look at the moisture level in the air, percent RH, 50% RH at 20 degrees C, 50% RH at 100 degrees C. The amount of moisture in the air is still 50%. But the amount of water is different at 20 degrees than 100 degrees. If you use RH as a sensor, you're going to have the same number, 50%, but not the same conditions. Remembering back your psychometric charts from school, if you follow across a psychometric chart, you have more moisture in the air at 50 degrees and 50% and 100 degrees than you do at 20 degrees and 50%. So RH is the easiest thing to measure. That's a cheap sensor. But if a customer tries to use that for controlling a fluid bed, and he said, well, it's 50%. It's 50% yesterday, it's 50% today. No, 50% yesterday was at 20 degrees. Today's warmed out. It's warmer out. Today's 30 degrees. You now have more moisture. More moisture in your air means you have less ability to dry.
Yes.
So that's why we don't like to use RH. RH is cheaper, it's easier to work with, but you don't get year-round, you don't get day-to-day. Literally day-to-day control will change. Afternoon to mornings will change. If you run a product in the morning, temperature is low, RH is 20%. Afternoon, it's warmed up outside. Now the temperature is 35 degrees. Your RH is still 20%. Different moisture levels. That means throughout the day, your product quality has been affected. Everything you do inside a fluid bed is to maintain product quality and consistency. The batch you run in the morning must be the same batch you run in the afternoon. So what we do is we use dew point. Dew point is actually a measurement of the moisture and the temperature. So we actually use dew point, which means a dual element sensor. I'm measuring the temperature and the RH, and then calculating it back inside the sensor to give me dew point. Much more expensive, much more accurate and reproducible readings. The sensor we use is a Vysula sensor that measures both temperature and dew point, temperature and humidity, and then calculates dew point. Most of the time we control dew point to about 10 degrees C. I say that, we got some customers actually run lower or higher. Usually for most pharmaceuticals, 10-degree dew point, year-round repeatability. Important to note, portable machines rarely have dew point control. Portable machines usually take the air from inside a room.
Yeah.
The room's already conditioned via the customer's HVAC, so we heat it only. We don't do anything with dew point.
Mm-hmm.
It's only when you start drawing the air from outside the machine, from outside the building, we do dew point control, either dehumidification or humidification. What else I tell you? Okay. If in the wintertime, what would you do? You would humidify the air to get back to your condition, right? In the summertime, you would dehumidify. We actually do both in the summertime, potentially. We always humidify the air above set point. So let's just say you wanted a 10-degree set point. You were running at 6. You would humidify to 10. Mm-hmm. That's what common sense says. Why go anything? You want 10, go bring it up. Only run one utility. If you're above, all you want to do is dehumidify. Run one utility. What we have found over the years is humidification has stability issues. So if you try to just humidify up to 10 degrees, you get a lot of this. It oscillates. It might only oscillate 2 degrees, but it oscillates more than we want. So what we will always do if we're below set point is we will actually humidify up to, set point is 10, we'll humidify to 15, and then use a chilling coil to maintain my 10. So you end up wasting some clean steam. What you end up getting is a much tighter, accurate control of dew point. Dew point control for drying, not that important. Dew point control for coating, which we're going to talk about a little later, mission critical.
Yes.
If your dew point fluctuates a couple of degrees, you'll get static electricity in your product, you'll get beads stuck to the side of the chamber. I'm pointing at Coral because she's reported all this to me and yells at me all the time. You'll get beads sticking to the inside of the chamber. So your dew point control is very critical for Worcester coating. Inlet temperature control we talked about. Face and bypass. We'll use electric heating on the smaller machines. Very accurate, very quick. The machine at Pfizer, I can get up to 115 degrees C. From ambient to 115 in about 5 minutes at full airflow. Very fast control, and I can still control plus or minus 1 degree. Questions on temperature control?
Yes. Actually, I had one question.
Go ahead.
Yeah. As you said, RH makes no sense because the temperature changed.
Right.
But what's the dew point sensor actually measured?
It's actually measuring two things.
Yeah.
In order to get dew point, you need to know the temperature of the air and the RH of the air.
Okay.
So the Weissmiller sensor inside of it actually measures both. Measures both, and then calculates. There's an equation internally. It then calculates the dew point based on temperature and RH.
Oh.
So it knows as the air comes across the sensor knows the temperature and the RH. It then calculates in real time, taking those two values, plug it to an equation, and spits out the dew point.
Oh, so the value on the screen is a calculated value.
Yes,
Okay.
based on RH and temperature.
Okay.
And it's all done internally at the sensor.
Got it.
That's why the sensor is relatively expensive sensor.
Yeah.
When you're talking to customers from processing, and your customer says, well, I'm trying to process now, here are my conditions. If he starts telling you I'm at 50% moisture, ask some questions. How are you controlling your moisture? Is it dew point or RH? Are you drawing from outside or from a room? A lot of times he's asking you to reproduce what he's doing in his room. He doesn't know his dew point
Yeah.
because it's not on the machine. It's Coral's Model 2. There's no dew point sensor on it. That's fine. Where is the air coming from? If it's coming from inside the room, Mr. Customer, your HVAC system, what is it doing? What's its dew point in the room? What's its RH or temperature in the room? Most customers that draw from the room have HVAC controls. The scientists might not know it. The building automation people will know it. And they can tell you what's going on in this room. So if you ask the questions, you can get the information needed to then reproduce it.
Yeah.
Because the last thing you want to do is move a product from R&D and then say, okay, you're running in a lab, and this lab is running, let's just say it's very cold in here. It's got a very low dew point year round. Now you go to production. Have you provided the hardware, the air handler, capable of matching the conditions? And if you can't match the conditions, how does that affect the process? You've got to ask those questions. Because a lot of lab environments although China's pretty good about it. A lot of lab environments I walk into are just downright cold. For some reason, they go crazy, and it's hard to reproduce that in a production environment. So you want to ask, what are your conditions in that room? Where's that air coming from? So you can reproduce it. It might need, instead of using chilled water, you use refrigeration, like air conditioning. You put a refrigerant coil in the air handler to get even lower dew points. Or you use a desiccant dryer to get lower dew points to match what they're doing in the lab. So Ricky, this is where Ricky, Frank, and Tony, Thomas all earned their keep, because you gotta start asking these questions. Customer brings you a process he wants you to duplicate on your machine. Well, I run this in my lab using what? How many times do we hear that? Okay. What conditions do you run it at? Well, we run it at we run it at 70 degrees C. Okay, that's the inlet temperature. What's your dew point? I don't know. Well, yes, you do. You have to ask, what are the conditions? Where's the air coming from? Well, from the room. Okay, good answer. What temperature is the room at? What's the RH in the room? If you know what the RH and temperature are in the room, you can go on, it's a simple calculator, I've got it on my machine. You can get the dew point. Now you know the operating conditions, the dew point and the inlet temperature. So when you go to run it back here in your lab, you have the same inlet conditions.
But I don't know how to calculate the dew point.
Not a problem. I've got, to be honest with you,
You can find the information from internet.
Yeah, maybe.
I've got a program, actually Vaisala, Vaisala, V-I-A, hang on a second. I'll tell you the company, it's a program I use. Hang on. We skip. Oh, good Lord, I screwed my. Remind me at lunch, and I'll bring the program up.
Okay.
I've got a program. Here we go. Programs. Vaisala, V-A-I-S-A-L-A, which allows me to calculate everything. So I can go in and enter values for temperatures, gas types, dew points, ratios, and calculate the missing parameters. Really a neat online or calculator. Calculates all very quickly. Same thing here. I can calculate. I can put my temperature and my relative humidity. Calculate my dew point. So let's say at 23%, 23 degrees, and I'm at 20%. There's my dew point.
Oh yeah.
Remember I told you the dew point changes based on temperature. So we're still at 20% RH. Let's go up to 55 degrees. Go. Let's go back to our 20%. Remember we are at -1 degrees dew point. Now what you're at. You haven't changed your RH at all. Your RH has stayed the same. But because you changed the temperature, your dew point has changed. So, very important. You can get this one online. Go to Vaisala's website. You can download this calculator. It's what I use. There's probably 100 different calculators out there. This one matches my sensors technology, so I get good readings from it. V-A-I. V-A-I-S-A-L-A.
Yeah.
And in fact, if I just saw it right, there's actually a language.
Yes,
yeah.
Chinese.
So I can actually change languages too. So don't ask me to do that because I had to make some more work for myself. Questions on the air handler? For drying, it's very simple. But as you start talking coatings, the air handler becomes more mission critical. Something to keep in mind on air handlers, we see every new customer is going to call you. You start the machine in the wintertime. They run their product in the wintertime. And they run that product in 45 minutes. They're happy. Spring comes. Well, you have two questions. back up a little bit. They run the product in wintertime. They dry the product, or done drying, they cool the product. Wow, they can cool it very quickly in the wintertime. Come spring, they can't cool it anymore. The temperature's not going down fast enough. Why is that? The fluid bed air handler does not have the capability to cool the air. All it can do is take moisture out of the air. Taking moisture out of the air cools the air. If there's no moisture in the air, there's no ability to cool the air, and your minimum temperature will change throughout the year. The lowest temperature you can achieve will change based on humidity, based on the moisture levels in the air. So usually in the springtime we get a phone call from a customer, hey, I used to be able to get a minimum temperature of 35 degrees. Today the best I can do is 40 degrees. What's wrong with my machine? Well, it's nothing wrong. It's a warm day outside, and it's a very low humidity air outside. So he can't get the low temperature. As the humidity comes up outside, as you cool the air, as you dehumidify the air, you cool it. But if there's no humidity in the air, your low temperature will change. HEPA filtration, we'll talk about quickly since we talked about it this morning, courtesy of our friends at Pfizer. HEPA filtration is the ability to basically remove particles from the airstream that are 0.3 microns or larger. Give you an idea how big 0.3 micron is. Consider this the thickness of your hair. Okay, so that's the diameter of your hair. That itty bitty black dot is about 0.3 micron. If you look at the scale, that's how small. So imagine that's your thickness of a hair. That little black dot is 0.3 micron. You'll never see it. Most pharmaceuticals filter the air to about, well, it ranges, somewhere around 99.5%. They want to remove everything that's 0.3 micron or bigger to 99.9%. That's how clean you want the air going into the product. So, we talk filtration, we're talking filtering to very, very clean. Even the Model 2, the Model 20, the Model 5s, Model 10s have HEPA filters on them. We actually put 2 HEPA filters, one on the inlet, one on the outlet. The one on the inlet is to give us clean air going into our product. The one on the outlet, giving us clean air into the environment. We don't want to be dumping your drugs to the environment. Who knows what you're making? It's another good one to ask you. When you start competing against other customers, other vendors, what kind of HEPA filtration are they providing? Are they providing HEPA filtration? Another thing I learned at the trade show last week with Tony and Thomas in Changsha, a lot of the vendors aren't providing outlet HEPA filters. That's the customer's responsibility. So it's always a good one to ask. Is the machine I'm competing against, are they providing both inlet and outlet HEPA? Yes or no? If no, great. Do you want me to take mine out of the price tag? Do you care about the environment? Find out what the customer wants. 9 times out of 10, when you tell him the difference and that you're protecting the environment, he's going to make the other guy come back with another price. Temperature control, dew point control, preheat, air filtration, all that's going on inside the air handler. If your dew point is too high, you can't dry your product.
Yep.
Water is, you can actually end up making your product more wet if your dew point's not being controlled. Your product will start absorbing moisture from the air. Too dry, you can create static charge, which we'll talk about in coating. Too dry for drying just means you dry faster. But it also means year-round you can't dry the same. Wintertime you dry in 35 minutes, summertime you dry in 45 minutes. Validation doesn't like things running different. But it is something a new customer will question you on. Hopefully not Pfizer. But a new customer who's new to fluid bed drying is going to ask you, why is it in August it took me 45 minutes to dry my batch? At the same temperatures today, my batch has taken 35 minutes. What's the dew point? Is the dew point too low? If it is, you're drying faster. Inlet temperature. If you're not controlling the temperature to set point, if you're too low, it take longer to get to your final drying. The temperature is too high though, it's also bad. You can damage product. So you've got to be able to control temperature and dew point. Usually we shoot for 2 degrees. Some customers want more. If they're willing to pay for more, we'll tune it for more. Tune it to 1 degree. You can also have problems with products if you dry them too fast. Remember yesterday I said coming out of the mixer, garbage in, garbage out. Take a golf ball size product, dry it really fast. Try to hit it with 100 degrees immediately. What happens is you dry the outside. The outside becomes a crust, becomes very hard. Now try to get the moisture out of the inside. You can't. We call that case hardening. So you want to dry at a controlled rate. Questions on temperature, heating, dew point. If not, we'll move on to airflow control. We talked a little bit about airflow control. We're going to start with a bypass machine. Start with a bypass machine. And we talked a little bit about this, courtesy of Ricky's question. But on a bypass machine, we've got a chamber airflow valve and a bypass valve. So the VFD is controlling the fan. The VFD is controlling it to a total airflow. So my total airflow, we make an example. My total airflow in this example is 2,000 SCFM. So this blower is controlling the sensor, or a sensor here is controlling the blower to maintain 2,000 SCFM. That means there's 2,000 going through the air handler. There's 2,000 going through the fan. The recipe, the customer has decided he only wants 500 through the fluid bed. Because his product, he's only using half the fluid bed. I'm going to adjust these two valves. I'm going to close this one. As I close this one's going to open. So I'm going to ratio how much air goes through the bypass and how much air goes through the fluid bed. So I've got another airflow sensor here that's going to adjust these two valves so I get 500 SCFM through the fluid bed, 1,500 through the bypass, 2,000 through the fan, and 2,000 through the air handler. Again, the reason for the total airflow control is because the air handler requires a minimum air to be efficient. Allows me to get turned down. I can usually get 10 to 1 turn down. So on a fluid bed, a Model 300 fluid bed, the one Tony loves, the Model 300 fluid bed, I can run at 3,000 SCFM. I can run at 300 SCFM. At 300 allows me to use very small batch sizes. I can actually do some R&D, some pilot work in a 300. So instead of buying a Model 120 and a Model 300, I buy the 300, I buy it with a bypass, I can now get 2 fluid beds. Same holds true for the 500. I can do a 500 to 7 tubes, but I can also put a 1 tube in it for coating. Now I get 5,000 to 500 CFM turned on. Still 10 to 1, but gives me the ability to run much smaller batch sizes. The customer gets 2 fluid beds for the price of 1 with the bypass. A little more work for me to do setting it up, but the customer gains a lot more turn down. As opposed to no bypass. No bypass is Pfizer. Pfizer's turn down is 4 to 1. They're basically 3,000 meters cubed as a minimum and 12,000 meters cubed as a maximum. Because there's no bypass, they get stuck with a 4-to-1 turn down. If I put a bypass in that machine, I can get down to 1,000 meters cubed per hour. Just by adding a pipe, 2 valves and a sensor. But this is where you're gonna be careful. If a customer's running production, maybe he doesn't want small batch sizes. There's a new job, this is where Tony, Thomas, Frank, Marco all earn their money, because this is where they gotta ask the customer, start talking to them. Okay, Mr. Customer, you want a 500-liter batch size. What's the smallest batch you wanna run? Do you ever plan on running very small batches? Do you think it's something you might want? Is it? We can put a bypass in. Ooh, your competitor can't do that. Too bad. We can. So now maybe you look more advantageous to buy us. Whether we're cheaper or not, we can give them the ability to run small batch and larger batches in the same machine.
Sir, I have one question.
Yes.
So, is it using the airflow sensor on the both sides, the bypass and?
Well, no, you've got one airflow. You basically end up with 2 measuring devices. One's measuring total airflow up here.
Okay.
One's measuring fluid bed, what we call process airflow down here.
So minus, so we
Right.
can get that.
So the process airflow is controlling these 2 valves.
Yeah,
The total airflow is controlling the blower.
okay.
So you end up with 2 control loops
Yeah.
to control the machine. This one is the process critical one. So this is the one that gets tested in IOQ. That's the one that's affecting your process.
Yeah.
This one doesn't have to be as stable, as long as this one is very stable. So you tune this one. What we end up doing is tuning this one
This RTT.
to be tight control.
Oh,
So fast control, we tune this one a little slower.
Okay, so I have a question.
Yes,
If 500 airflow is required in the chamber,
yes.
you say, but the total airflow can be 1,000 or 1,500.
Right.
Right, but how to control? You
Well, the machine, the engineering team has decided what the minimum airflow is through the air handler.
Mhm.
Okay?
yeah.
So that sets the total airflow.
Mm-hmm.
The total airflow is controlled via the VFD on the blower.
Yeah.
So the blower is speeding up or slowing down to maintain the total airflow.
Okay.
You have an airflow sensor right here. That airflow sensor is adjusting these valves to control the airflow through the chamber.
Mm-hmm.
That's the one you set in the recipe. So the recipe will ask you for process airflow.
Yeah.
Because that's the one that's critical to the product. That's the one that's going to affect product quality. So the customer sets this one. These valves adjust automatically to maintain it. The total airflow is set via the machine itself. All,
Okay.
and the customer never has to see it. It's all done automatically for total airflow.
Yeah.
I don't think I answered your question. Ask your question again.
Oh, sorry. I mean,
No, that's okay. I answered it. That's
Yeah.
the way I thought, but the look on your face says I didn't answer.
yeah. I mean, so we said the airflow we need is 500.
Right.
Yeah. This is go through the plenum and the chamber, right?
Right.
Yeah. But there is a bypass, and the total value can be 1,000 or 1,500. Yeah. But how the fan adjust?
Which valve?
Yes.
Which valve?
Which one?
Remember, okay, think of it as 2 separate controls.
Okay.
Think of it like an air handler. You've got temperature and humidity.
Mm-hmm.
Think of it the same way. Now you've got total airflow, chamber airflow.
Yeah.
So the total airflow is set via the size of the machine and the efficiency of the air handler.
Mm-hmm.
So the total airflow, some air goes this way, some air goes this way.
Yeah.
All of the air is right here,
Yeah.
right? So there's a sensor here measuring total airflow.
Yeah.
That sensor is controlling the speed of the fan.
Yeah.
So the fan's going to speed up or slow down, so the total airflow is at set point, automatically.
Yeah.
Okay?
Mm-hmm.
Now the process airflow, which is set inside the recipe, is set for, you said 500.
Yeah.
So now the machine is going to automatically adjust these valves. Those valves are actually connected together. So as one open, one closes. They won't close all the way,
Oh.
but they'll ratio. If one's 50% open, the other one's 50% closed.
Okay.
If one is 70% open, the other is 70% closed.
Oh.
So they're inverse valves
Yeah.
using the same signal.
Oh, so we can also set the total airflow value
Yes.
on the screen.
Well, it's set via engineering.
Oh, yeah.
The customer doesn't set it, engineering sets it.
Okay, I know.
Yes.
Yeah, clear.
Okay.
Yeah.
This to me is fantastic. This gives Tony, Thomas, the sales guys, something to talk to customers about. You want to buy a Model 300. Okay. Damn good machine. But you're going from Model 2 to a Model 300. How are you going to do that? I don't know. Do you want to put a Model 100 bolt in the Model 300? Wow, yes, I love that idea. I can now do R&D, pilot, and production in 2 machines. They don't need to buy a new air handler. They don't need to buy a new fan, a new chamber, a new room. They use the same air handler, the same fan, the same sensors, the same process room. All they do is buy a small bowl and a big bowl. Big bowl for 300, for production batch. When they run a smaller batch, they push the 300 bowl out, push the 100-liter bowl in, and now they have a pilot scale machine in the same room. It's tough to explain to customers. This is one we've been trying a while here to try to explain to customers, is they don't need to buy a Model 120 and a Model 300 unless they plan on running both machines at the same time. If they're not running them both at the same time, I can give them one machine to do both and save them a lot of money. Not just on, remember, money's not just a machine. The machine is a small part of an area. They've got to build a room. They've got to pay for construction. They've got to pay for the air handler in the room. They've got to maintain the room. So instead of being 2 machines, it's 2 machines, 2 rooms. Much larger building. If I can give them the same size machine but 2 bowls, I save them $300,000 on a machine. I probably save them $500,000 in the room. I save them $1 million immediately. Thomas is now a hero. They buy 2 machines, they're happy. So this is where you got to know what you can do and question the customer. Mr. Customer, why do you want a 120 and a 300? Do you want to run both machines at the same time? Because if you don't, I got something I can offer you that'll give you both machines for half the price. And I've already built it many, many times, so what's your competition going to do? They can't touch you. And I've actually got a picture of it, and I'm actually going to jump ship and show it to you since we've been talking about it. Let me jump out of this one for just a moment. We've been talking about it. Let me show you what this looks like with the bypass. SimCam. So here's a machine with bypass. Same machine, same building, same customer, same everything. The picture on the right is a 300-liter coating bowl. 3 coating partitions, 3 everything. That's their production machine. They actually make morphine in this machine for pain injuries. The machine on the left is the exact same machine, same control panel, same chamber, same fluid bed, same everything, other than a different bowl. That's a 1-tube bowl inside that machine. The reason that works is they have a bypass. They can run the machine on the right. I think they run it roughly 3,000 SCFM for production. But they can run the one on the right down to 300. I'm sorry, the one on the left down to 300 and do pilot scale work in the same machine. Just by using the bypass. The bypass lets you go roughly 10-to-1 turn down on airflow, whereas a standard machine is roughly 4-to-1 on turn down. That is huge. You'll see this, Arvin, especially when you run the Model 2 in your lab.
Yeah.
When you try to run 100 SCFM, your temperature control is really good, really fast.
Mhm.
Go and run it down to 10 CFM. There's no bypass in that machine. The temperature control is very slow. And you'll see this when you start running back there. It's because 10-to-1 turn down, you lose the efficiency across the air handler. Using the bypass, I keep all my efficiencies. Most machines, like I said, are 4-to-1 turn downs without a bypass. With the bypass, I get 10-to-1 turn down. I wish we could sell this to every customer we talk to here in China. It's getting them to understand, unless you run that machine, unless you're gonna run both machines on the same day,
Mhm.
and you're gonna do that almost every day, I can save you almost everything by buying this machine. And I can do the same thing, in fact, I've done it with a 7-tube machine, so 7 coating columns, Model 500, and a Model 100. I can do the same thing on a larger scale. Let's customer do a lot of development work in one machine. So we talked about it, but here's a write-up for it. Total airflow control without a bypass. You got a blower. This one says blower valve. Nowadays it's a blower VFD. Increase the speed of the VFD, increase the total airflow without a bypass. Problem with it, you don't get 10-to-1 turn down. With the bypass, a little more hardware, because there's one more pipe, 2 more valves, 1 more sensor, more software. But it's a one-time cost. Now you get 2 machines. Basically, you get 10-to-1 turn down instead of 4-to-1. That is significant to process performance and allowing your customer to run a smaller batch and a large batch. If not, instead of, picture it this way, instead of running a 100-liter batch and a 500-liter batch in the same machine, now he can run a 500-liter batch and a 250-liter batch with or without a bypass, which means it takes more products, more product, in order to do R&D work or pilot work. What if he's got smaller batches he wants to run? What if he doesn't plan on running 500 liters all the time? He wants to run 100 liters. He's got small production batches, 100 liters, and large production batches at 500 liters. Everyone here thinks 2 machines at that point. I can do it in 1 machine. Now, sales doesn't like to hear that because sales wants a $2 million order, not a $1.5 million order. But imagine how much easier it is to sell when you walk into the customer and say, I can save you millions. I can save you $500,000 on the machine, and I can save you $1 million on your room. Because now it's 1 room, not 2. Huge difference. Questions on temperature or airflow control, with or without a bypass? See, this is what you got to remember, Ricky. When the sales guys come back and say, I need you to quote a 120 and a 300. Hey guys, if you ask the customer if he plans on running both of these simultaneously, or does he really only need 1 machine?
Yeah.
Oh, wow, we never asked him that. We can go ask him.
Okay.
The guys, you got to keep working that way because there's a lot of angles that we can get more sales.
Yes. Yeah.
Okay, we're talking about the air plenum. One of the things Fluid offers that is unique to industry is we use a hydraulically driven agitator. So the agitator is this rake inside the bowl that slowly turns through product to ensure wet material stays fluidized. So imagine, if you will, you load the fluid bed. Two ways to load a fluid bed. You can vacuum load product into it like we're doing at Pfizer. So the product comes in, it's always moving. No need for an agitator, it's always moving. But imagine if you push the bowl under the mixer, discharge product out of the mixer into the bowl. All that weight sitting on top of it, squishing it down. You then push the bowl into the fluid bed and try to fluidize it. Don't care whose plate you use, I don't care if it's a gill plate. You get a compressible product like Pfizer's product, it won't all move. What do? A lot of people will run the first 15 minutes, stop, and actually manually fluff the bowl to get it moving. What Fluid Air offers is an agitator drive system that will slowly turn through the product to avoid what's called rat holing or channeling. Channeling is when the air breaks a hole in the product but doesn't move all the product. So we call it like a rat's hole. So in our air plenum, in this picture here on the right, the air is coming in through the inlet pipe, comes in through the plenum, and up through the bowl. Inside the plenum is a lower agitator drive, which is going to turn the agitator inside the bowl. Now, how does this work? Well, here's the inlet pipe, here's the air plenum. So and on this machine, it's a portable, or the bowl is portable. We push the bowl in, the plenum raises up, picks the bowl up, and seals it to the chamber. As the plenum comes up, it aligns with the inlet pipe. There's a gap here. There's an inflatable seal that then inflates to form an airtight seal between the inlet pipe and the plenum. This way all the air is coming through the inlet pipe, not from the room into your process. And of course you've got a lower agitator drive. If someone said lower agitator drive, there must be an upper agitator drive. So here's the upper agitator drive on the bowl. So the lower agitator drive has arms going this way. Those arms engage the upper agitator drive, turn the upper agitator drive, which in turn turns the agitator. All automatic, all automated, all designed with static protection and safeties so that there's no static charge, no spark. We are the only one using a hydraulic agitator drive. Why use hydraulics? Why not use compressed air?
More power,
More what?
more torque,
More, go ahead, say it.
torque, more
More torque, yes, more torque, yeah, absolutely. Compressed air in a facility is usually 100 psi, maybe 120 psi. My hydraulic system create, well, for agitator I use about 1300 psi. So the product's not all fluidized, the agitator would hit it, push it around, and get it moving inside the chamber. Unique to industry. Now, most customers I'm finding out in China like to vacuum load products. If you vacuum load from a mixer to a fluid bed, the agitator really is not that valuable to you. The agitator becomes valuable when you're not vacuum loading. It becomes valuable if halfway through your dry, you stop. Pfizer's done this a couple of times. They like to do inspect icons. So they stop the fluid bed. They vacuum load, great, no agitator needed. But then they stop, they 5 minutes into the batch, they stop the fluid bed, they pull the bowl out, they look at the product. Looks good. They push the fluid bed bowl back in. You now have 1,000 kgs of product squeezing itself together. So the very bottom of the product is compressing itself. The longer you wait, the more compression on it. Push the bowl and try starting it. What they saw happen is the product starts to move and then boom, it blows a hole in it.
Yes.
But this little product here didn't move. The air in the machine will always take the path of least resistance. So where the product is moving is where the air is going. This product's not moving. It's not going to move.
Yes.
And they had, at the end of the batch, they had product stuck there. They had an agitator, we could have turned it through the product and moved it. Now Pfizer's solution says that they're not gonna stop the batch halfway through, so it's okay. This was just a one-time deal. So agitator, that's something to keep up and think about. If agitators, if they're vacuum loading, maybe we remove the agitator from the quote. Remove the agitator from the quote, we can save about $30,000. Might make it easier for Thomas and Tony to sell. If we're not using the agitator. So what Pfizer did. Pfizer's original quote had an agitator on it. They kept saying, we don't want, we don't want, we don't want. We said, well, you understand what's going to happen. They said, yes, we don't want it. So we removed it. That lowered the price of the machine, both for us and for the customer. So it's something to keep in mind. A lot of moving parts on the agitator. There's a hydraulic pump, obviously mechanical space, but hydraulic pump is sending fluid up through these lines. There's a motor underneath this cover. That motor turns this agitator drive at about 10 RPM and then drives the agitator. The agitator basically is just a rake to slowly turn through the product to make sure it all moves. Normally when it's assembled, right now I've got it sitting on a floor for the picture. Normally the agitator is down on this lip seal so you don't see it. And these fingers are lowered down to within about 1/4 inch off the bottom of the plate. So don't be confused by this picture. I couldn't hold everything together and take a picture, so I had to set it on the floor and I had to push the agitator rake up a little higher than it should be. Product bowl. There's not much to the product bowl. It can be like Pfizer's on a swing arm that we push in and out. It can be like Corals that we pull in and out. It can also be a full bowl that we roll around the room like Pfizer's first model 500. A couple things most bowls have. Sample thief, product temperature probe. The sample thief can be, in this case, the customer slides the thief in. While they're running, product fills the void. They pull the thief out. They put the product in a container and take it to the lab for testing. Sample thief allows for in-process, real-time product analysis. When we offer two types of sample thief. We offer this one here that's open. We can actually do an enclosed sample thief as well. I saw a lot of enclosed sample thieves at this year's trade show. I'm curious, is that going to become a norm, you think, Thomas?
Well, I didn't see.
Oh. I'll be curious if you start talking to customers if they think that's something they insist on now. I saw a lot of enclosed sample thieves at this trade show last week. Be interesting this year as you talk to customers to see what they want. Because ours is designed for an OEB4 machine. Very expensive. It's got a little vacuum, it sucks product out of a little container. But the ones at the show weren't OEB4, but they were still an enclosed system. That would be interesting to see if customers want more of that. So here's a slightly better picture of the agitator rake and the inside of the filter bowl, of the product bowl. The product bowl uses a plate. The air comes in, turns 90 degrees one way or the other, then comes up through the product bed. That turning of 90 degrees creates pressure drop, which ensures the air tries to fill all the voids. It also creates turbulence. That turbulence helps to move product off the filter plate. This picture is kind of misleading. I use the word turbo flow bed plate. Turbo flow is the manufacturer's name. Nowadays, probably the last 15 years, the plate we use is called Conador. Again, Conador is a manufacturer's name. Conador is pretty much the industry standard. The reason for that is Conador creates a very high tolerance plate. If they say it's a 20 mesh opening on that plate, it's a 20 mesh opening.
Ron, can you spell the vendor's name?
Conidor,
Yeah.
Conidor, kind of the bird Conidor. Both plates, whether it's TurboFlow or Conidor, are manufactured out of a heavy gauge stainless steel. It's designed to create a pressure drop under the plate so that the air fills the void. Because imagine, if you will, the air is coming in from the back of the plenum. It's coming in at 3,000 meters cubed per hour at pretty high velocity. All that air wants to go all the way to the front of the plenum, hits the front of the plenum, and bounces up. So the air really wants to go to the front of the bulb. We don't want it there. We want it equally distributed along the bottom of the bulb. So what we do is, by using the filter plate, is we create a pressure drop. By creating a pressure drop, the air hits the front. It can't go easily straight forward, so it then backs up and fills the plenum. So now the air plenum has air all the way around it going up through the plate. I call it a waffle design. A waffle design simply means that the air is coming up. It can't go straight through. It hits the piece of stainless steel and has to go left or right. Each one of these is opened on both sides. So the air's got to go left or right, creating the turbulence and the flow patterns. A little different than, I know Gia and some of them use a gill plate. The gill plate creates a nice swirl action, but still creates dead spots along the edges. That's the reason why we never got really like the gill plates. A real simple animation of the agitator. So in a normal operation, the idea is to have all your product moving like this. But you can very easily get a spot that doesn't move on a standard filter plate. So the agitator slowly rotates through it, pushes that product. Once you start moving the product, it breaks free and starts to fluidize inside the chamber. Again, the agitator is an option. If you're vacuum loading, I can see a lot of customers in China not using it. Most customers, kind of funny, Europe, North America, South America, probably only 30% use vacuum loading. Most customers push the bowl under the mixer, dump it into the fluid bed, push the bowl back into the fluid bed. China really likes vacuum loading. I know why. It minimizes contamination. If you've got an operator and he's picking his nose, or he's got his pen. I got a bad habit.
No, we have a clothes. No.
My bad habit, I put my pen behind my ear. Well, if you look over the bowl, your pen just fell in the bowl. Bad habit. But in China's like South America. They're worried about contamination. They've had a lot of historical contamination issues. If I use vacuum loading, I go from one sealed machine to another sealed machine. There's no way to contaminate it, no way for the operator to contaminate it, no way for the room to contaminate it. So I see more, in fact, every product we quote here wants vacuum loading from mixer to fluid bed to mill, which is great. It's a little more expensive, a little more engineering, but I understand why. It's contamination. So if you're doing one with vacuum loading, it's worth asking the customer, do you want the agitator? If you don't need it, don't buy it. If your competition's not bidding it, if he's not bidding an agitator, why would you bid it? Why add more money to your bid if you can't get something for it? And like we saw at Pfizer, as long as they vacuum load, and as long as for the first 20 minutes you don't stop the fluid bed, they don't need an agitator. If they stop it in the first 5 minutes, oh Lord, they need an agitator. The other nice thing about the agitator is I can make a slight modification to it. Instead of being a straight rake, like you see in this picture, I can do what's called a discharging agitator. So now I still have the rake on the top, but now I sweep it. That sweep allows me to actually empty the fluid bed without using a bottom discharge. So here you see this is Pfizer's Model 500. The bowl is pushed in During discharging, I turn the agitator counterclockwise. Because of the sweep on the blade, it pushes product towards a discharge valve. That discharge valve, right here, is connected to a vacuum, and that sucks the product out of the bowl to the next machine. This is great for customers who don't have a tall room. Who here has been to Pfizer? Thomas has been. You been to Pfizer?
The current with by
Yeah, you
500
went.
model.
You went
Our
for
brand.
the vending.
So if you go to Pfizer, Pfizer's room right now is basically 14, 28. It's got to be probably 35 feet tall. And what so 10 meters, probably a 12-meter room. That room is a very tall room, and they actually charge from the top of the room to the mixer, from the mixer to the fluid bed, from the fluid bed to a tote.
Yeah.
Great. What if that room was an old room like this where you don't have 14 meters? You've only got a 10-meter ceiling. You can't do that. So what they've done here, this is Pfizer's Model 500 at the old building, is they use a side discharge. When they're done drying, ready to discharge the machine, this valve opens, the agitator turns, pushing product towards this flush-mounted port, pushes product to the port, the vacuum sucks it up to the blender. That's the other advantage where a discharge or an agitator helps me, is I can use a discharging agitator to discharge the bowl. And I'm kind of, go ahead, you have a question, Diane? Okay. I've kind of gone back in reverse order. I showed you how to empty the fluid bed bowl. I haven't showed you how to load the fluid bed bowl. Just like loading the mixer, there's a couple ways to load the fluid bed bowl. We can, as we talked about, push the bowl, push the bowl underneath the mixer, open the mixer valve, dump the product to the bowl, push the bowl back to the fluid bed. That's about 80% of North America. Probably 80% of Europe. South America and now China really likes vacuum loading. So in vacuum loading, what we do is you push the bowl into the fluid bed, seal it up, turn the fan on.
Yeah.
Remember, the fan is on the outlet of the chamber. That means I can create a vacuum in the chamber. Well, if I connect a hose to the bowl, this hose is now a vacuum. It'll suck product into the fluid bed while running. Now this picture actually shows us we're going to discharge to a mixer, to a mill, the mill to the fluid bed. But you can very simply take this hose, connect it directly to the mixer, and vacuum load it out the wet mill. So two ways really to load a fluid bed. One, to just drop the product into the bowl to push it in, or you can vacuum load. Vacuum load has a couple advantages. Not only do you protect your material from contamination, hairnets, pens, whatever, you protect the operator from the product. 26 years doing this, most of the products we used to do are pretty safe. A lot of the new products, in their raw forms, are mutagens, carcinogens. They're dangerous exposure to the operator. So if you're going to open a machine up and dump it to the bowl, the operator would have to wear a PAPR suit. He'd have to wear an oxygen mask. He'd have to wear this heavy clothing to avoid him being hurt by the product. It's still a risk. What if his uniform's put on wrong? What if he tears it? Now he's exposed to a dangerous drug. Using vacuum loading, like which China loves, man, your customers love vacuum loading. Now you protect the product and you protect the operator. You also protect the room. You can't spill product to the floor if the product's never open to the room. Spill product to the room, you run the risk of someone walking it to the next room. So some great advantages in vacuum loading. There's some cost associated with vacuum loading. I need to modify the bowl with more hardware. Obviously the piping. I've got to add one valve to the fluid bed. For vacuum loading to work, you need to control how much air is coming through this pipe and how much air is going through the bowl. The reason for that is you want the product inside the chamber to keep moving. You don't want the product to come in, stop, and fall on the plate. That would defeat the purpose. So what we do is we use a valve right here. Let's say there's a valve here. Excuse me, I can proportional the valve to control how much air comes from the hose and how much air goes through the chamber. That allows me to control the fluidization while I'm vacuum transferring. So now I've got enough vacuum to move the product and enough air to keep the product moving in the fluid bed by controlling the position of a valve right here, the vacuum load valve. I never used to like vacuum loading. Watching it run now at Pfizer, I like it more and more. The reason I never liked vacuum loading is the problem you see in this picture. That's an awful lot of hose to clean after every batch or after every campaign. This customer, this is actually my facility. What we ended up doing is making this hose shorter, save money, and then we dedicate the hose to a product. You could clean it, but how do you swab test 10 feet of hose? You can't. So what we end up doing is dedicating the hose to a particular product. Pfizer doesn't work. Pfizer's got a 4-foot stainless steel pipe that we wash down. It's stainless steel, easier to clean. Air handler, fans, airflow control, temperature control, dew point control, agitator, vacuum loading. All makes good sense? Kind of understands it? Any questions?
So, 没关系，您说吧。
Actually, I have a question about the bottom discharging of Pfizer.
Sure.
I don't know how it works because it's the plate, you know.
Sure.
And-
I don't have any good pictures of it either. Yes, I do. Hang on. I do.
Okay.
Second here. Pfizer's fluid bed. In English.
当时好像那个人没给。
I like picking on corals. These are my favorite things.
Yeah, so there's the hydraulic pump side of the screen that the hydraulic pump will drive the screen to let the
但是
product
它那个底盘怎么弄？因为底盘一直在里面，它是一个完整的。
对，旁边有一个液压泵，然后它会驱动那个底盘翻转，然后上面物料就比较轻。
但底盘是有气密封的呀，真的。
气密封解开就可以了呀。
不是，是这样的，我意思是，它跟那个正常这是锅嘛，那个底盘应该是直接就是整个覆盖在上面，转是转不动的呀，被那个锅体应该是挡住的。
就是它跟那个锅体之间是只有一个空气气流分布盘，对吧？然后侧边是气密封，侧边气密封是相当于把这个气流分抱在那边的。
啊，你的意思是它这个就是说一个圈儿，然后它一个圈儿外边是一层气密封。我之前
所以它带动它，然后它就可以翻转。
我一直以为它是这种挡在这儿，然后这么密封的，这种密封，然后它转不动，这样。
对，它这是实在是可以转动的。
I don't know if I trust coral.
Why?
Why? Why would I not trust coral? Teasing you, Miss Coral.
I think they already show us how
You-
how it works.
因为当时
Well,
那个
yeah, basically what you have, and I'm trying to get a picture so I can show you.
当时在现场没有问太多嘛，那时候。
Hang on, I got plenty of pictures. I just gotta be careful. I don't want to show you the wrong picture. Don't want to introduce you to my girlfriend. Of course I have lots of girlfriends.
The file name.
You mean this one?
Do you have the picture of the?
我主要是想看它底盘那个，对，像 Cora 那么说的。如果那样的话，就我都能理解了，直接就转一下就行了，是吧？就可以出料了。
Second here.
出完到哪里去？
就下面这个鬓筒直接接住了，
然后并再接到干整。
对。
对。
因为之前我从来没接触过这种底部出料的。
There's Mr. Henry.
All right.
Mr. Henry posing by his machine. Okay, so here you go. So here's a Pfizer's current 1,000 liter machine. What you have on the bottom here is a filter plate. This filter plate, you can kind of see a hinge pin here, is attached to a hydraulic motor. So when you're running, the plate is closed. We inflate a seal around the plate, so,
Okay, yeah,
it's held in place. When they go to discharge, we deflate the seal. That allows the plate to now rotate. We then use a hydraulic motor here. It's an air-over hydraulic. That rotates the plate 90 degrees, allowing product to then fall through the plate. Product then falls through the plate, through the air plenum into a tote below. And then they move the tote over to the lift for bottom discharging.
Yeah, I know. Carl just explained to me that this is
There we go.
this seal.
Here's the bottom of the filter bed of the bowl for bottom discharging.
Use vacuum loading.
So here's the bowl.
Grab.
Here's the top of the bowl.
Mm-hmm.
Here's the underside of the bowl. So here's this big hinge pin. This hinge pin is connected to these bars. These bars are connected to the plate. During discharging, so right around here is the inflatable seal. Right here. Right now, right there is the inflatable seal. It's deflated. This entire plate is going to rotate slowly 90 degrees to allow product to fall below. You can see how beefy this plate is, because this thing holds 1,000 kg, so it's 1 ton of material on top of it for bottom discharging. Then when the plate rotates closed again, once there's a sensor that tells me it's fully closed, once it's fully closed, I inflate the seal again to seal it airtight.
This plate is
Yeah.
cleaner.
Clear.
So why don't we do this? It's 9:30 now. I'm sorry, it's 10:30 now. Why don't we meet back here 10:45,
Okay.
and we'll continue forward. Good chance I'll get a cup of coffee, stretch your legs.
Okay.
What?
Clean the water.
Yeah.
No, you started answering questions in Chinese. I don't know what you're answering.
Okay.
Okay.
That
Okay.
means
I mean the.
No, I've not
Here,
learned my Chinese
this is
very
the-
well at all. I am more stupid than I was
Do you
yesterday.
know,
No.
do you know
This
your,
is-
Dave can
You
write
just see this one.
Dave is fantastic. I think Dave
Oh,
Dave will
yes.
pass his class.
This is
Dave
Yeah,
wanted
this one.
Dave
I know,
wanted to
I know,
take the
I know.
HSK
Spoon
test
back
last Saturday, but he
Yeah,
didn't-
yeah,
he-
yeah.
to the end.
the test was on
Oh.
Saturday and he left on
I
Saturday,
think you
so he couldn't take the test.
like
Dave has
This
done
is the bowl. I
fantastic.
can pull it out and then
He took the first class here,
my question is
started the second class, went
when
home, and was
discharging,
taking the second class
plate
using
rotate
WeChat
90
at
degrees.
4 in the morning.
We don't
Chicago
need to
time.
put
Oh.
So we continue taking classes 2 or 3 days a week.
the,
from Chicago,
the
from
product
home.
will fall down.
Came back
down
here,
to the
and while he
to
was
the
back
base.
here, he was working again,
water we fix
But
working on
this
section
part
2
should be
of
clear.
his Mandarin.
I got that one.
Done
Yeah, there's
fantastic.
something on the here. This is a
Um,
place.
Oh,
The lid will be first before that close.
Okay.
this should be
Now,
open.
he has
Okay.
the advantage. What's that?
Okay, understand. Okay, thank you. Oh,
Yeah.
that's good.
Dave has an
It's
advantage
difficult.
over me. In the
This is
evenings,
different.
Dave finishes at Pfizer. He goes back to the hotel, he's got nothing to do. In the evenings, I finish at Pfizer, I go back to the hotel. I have work for Thomas and Tony to do. I have work for Pfizer to do.
Yeah.
I have work for Ricky to do.
Oh, Ricky.
Ricky is in trouble.
No, Rick, the whole team's been fantastic to work with here. Let me think about this. Right now, I transferred Glyphosate. Glyphosate's only 800 kg, a little smaller batch. This one, if I had to think about it long enough, I'd say this one's probably 20 to 30% slower. So what I do in 10 minutes using gravity and a 10-inch pipe is going to take me 13 minutes through the 6-inch pipe in this configuration. I'm not sure if it's the 6-inch pipe that's the restriction, or the fact I got to suck it from below. It's probably a combination of both. Smaller pipe and the added force needed to lift it. So it's probably a combination of both.
And one more, when is the vacuum load, if it is in the filter, so it will be the, if it is the rotary, don't have the agitator, is it required the agitator for this one?
Well, no, we said earlier, if you're vacuum loading product, the agitators really have not a value.
I'm not sure.
The agitator is a value. In this configuration, I take the bowl out of the machine, and I push it under the mixer, and I discharge everything into the bowl, and then I push the bowl back in. I have to get everything lifted off the bowl. That's when the agitator is a value. If you're vacuum loading everything, the agitator really isn't the value, unless you stop the batch.
Yes.
Pfizer stopped that batch, the 900 kg batch. They tried stopping it in the first 5 minutes to look at it. All that wet material then sat on a plate. It was difficult to get moving again and get all of it moving. That's when you use the agitator. If they vacuum load like Pfizer's doing right now and everything's vacuum loading, the agitators have no value, which is why they didn't buy it. We originally had an agitator in the quote. They said they didn't want to save money, so we took it out. And as long as you vacuum load, there's no need for an agitator. And that's because the air or the product is coming into the machine and is always up here. It's not sitting down here. The only reason the agitator is a value is when you start with product down here. Then the agitator is a value.
One more, the last
Sure.
question.
No, please,
There's different
ask away.
question. Yeah, you told about the 80, we can create the 80% in the vacuum in the chamber, right?
I can create what?
80% of the inlet valves, air inlet valve we can close. We should not close the 100%.
Yeah, you can.
Yeah, we should. I
What
think
value
as a
would
safety
do
feature.
you? If you closed it all the way, you would have a lot of vacuum here, but very little fluidization. So you'd move all the product in, it'd fall down and sit here.
Yeah.
So it wouldn't do you, from a processing standpoint, it really wouldn't help you. You've defeated the purpose of the vacuum load.
Okay.
The idea of the vacuum load is to adjust the valve and the airflow so the product moves through the vacuum very efficiently and it stays moving in the fluid bed. If you put that valve at 80% closed, you'd have very little air in the fluid bed and everything in the pipe. So it would transfer very quick and sit there.
So you mean during this transfer, the process is also working?
Absolutely.
To
Absolutely.
Save the time.
The only way for this to work, the only way for vacuum load to truly work and be a benefit is if you keep the bed moving. If all you do is suck it in the fluid bed and leave it sit there, you've kind of defeated the purpose. So you adjust the valve and you adjust your airflow set point through product qualification testing to figure out the right values so that the product moves efficiently and is staying fluidized in the chamber while you're moving it.
Okay, I got it.
Yes?
For the aisle handle system, is it standard parts or special design for just for our fluid bed?
It's actually a standard air handler. We have in the past purchased an air handler here in China. Janssen & Johnson up in Xi'an We actually bought the air handler here locally. So it is a standard air handler. The difficult part about it, we've been having problems right now, and something Walt and them are trying to localize, is trying to buy an air handler quality. The one we bought for Jansen was, did not live up to the quality expectations. And that's just finding the right vendor. If you can find, and that's something to think about. The first couple of machines we built here, which we are working on doing now, more than happy to go out there and look at machines with you. If you find a vendor who makes air handlers and you think they're worth looking at, obviously Bill and yourselves can go look at the equipment, go to their factory. I'm going to be here forever the way Thomas keeps selling to Suzhou. I'm more than happy to take a day off, whatever I'm doing, and go with you. We've used other manufacturers of air handlers, and we've used some bad ones. The air handler we use now, we've been using probably 20 years. Not the cheapest, but their quality has been fantastic on every job. I've never had one where I've really been disappointed. So you should be able to find air handlers here that meet my quality. I've seen them at other facilities in China, so I don't see that being a problem. So you can buy air handlers here. Most of the sensors I use are global manufacturers. Pyromation, Thermal Instruments are all made globally. So, in fact, we use the Shanghai calibration site here for my mass flow. So you should be able to find the exact same sensors that I use and buy in the US. You should be able to buy here. Exact same model number, exact same everything. Which will save a lot of money and a lot of challenges. You can buy them here. We can tell you what sensor to buy. You buy it here. Same vendor. Air handlers, plus we buy VFDs. The variable frequency drive is an Allen Bradley 735 drive. I can buy it in the US and ship it here, we just buy it here. It's the same drive. So there's a lot of things like that. We trying to make, in fact, the odds are if I buy it in the US, it's probably made here anyway and sent to me. Everything is made here. So you should be able to find everything. My valves. The valves I use are Bray valves. We should be able to buy them here. The only thing I think that will be challenging to buy here is a bought part. Is going to be the fan. The blower on my machine is a custom-made blower. I have tried various fan manufacturers in the US. I keep going back to 2 or 3 of them. The only 2 or 3 I've had that ever built me a fan that I like and works to design. So that we might have to buy from the US. The small machines, the Model 2, the Model 5, the Model 10, the 20, and the 50 are blowers that you can buy. They're regenerative blowers, kind of like what you use out here on some of your skids. So we can buy those here. It's the real big blowers. I mean, this one here at Pfizer is 200 horsepower. Diad?
Yeah.
How many horsepower is the blower at Pfizer?
Yeah, 250.
250. So a 250 horsepower blower, that's a custom blower. But the smaller ones on the smaller machines, it's a regenerative blower. You use regenerative blowers right now out back on some of your equipment. So we should be able to buy that locally. There's a lot of things here that you can buy the exact same model number that I would buy in the US that you can buy here. The control components, solenoids, relays, Allen Bradley parts, exact same stuff you can buy here. So the big challenge is going to be the blower, and it's going to be finding the quality vendors. Because every vendor says they have the greatest quality. You're going to go through a few, you're going to go buy one and go, well, that's a piece of junk, and have to work it. You're going to have to learn like you do on everything else. Once you find a vendor, you've got the vendor. Fabricated parts are real challenging. Some of the stainless steel work will be challenging. Some of it you'll be able to do here, some of it you have to buy from my vendors in the US until you find your vendors here. I don't find the localization to be that difficult. There's a lot of man hours finding vendors, qualifying vendors, reviewing their work. Once you get those vendors, once you find vendors you trust and who understand what you want, you're I've used the same stainless steel vendor for 20-some years. Not the best price, but definitely the best quality. So, it's not something you can't do. And again, if you want to look at vendors, you want someone to go with you to look at air handlers or blowers or stainless steel work, obviously, I mean, Tony, Thomas, Bill all know how to reach me. I have no problems leaving Suzhou for a couple of days. Thomas takes me all over the country. So if you need help, more than happy to help. I'm going to actually skip the next couple slides and come back to them because they have to deal with coating and talk a little bit about the fluid bed chamber. Chamber, obviously, on fluid air is, well, used to be very unique. We're starting to see more and more copycats. In fact, our friends in Germany used to use a chamber as a perfect cylinder. Easier to manufacture a chamber. Make this a straight cylinder, real easy to fabricate.
Yeah.
You roll it, you weld it, you're done. Making a conical section, now is a lot harder to roll, a lot harder to weld, a lot more surface area. But there's some significant benefits. Remember I told you our chamber's been designed so that top spray granulation, Worcester coating, and drying all use the same chamber. The real advantage of my chamber is this picture here. From an engineering standpoint, think about it. The air comes through the plate here. This diameter is fixed. It's the size of the bulb. So right here is 100% velocity. As my diameter changes, my velocity decreases. Think of an airplane. As velocity decreases, the lift on the airplane, what makes the airplane rise, the lift goes down as the velocity goes down. And in fact, it's the velocity squared. So small changes in velocity have the squared effect on the lift. What that means is my particle goes up in the chamber. 100% lift. It takes off fast. But as the diameter changes, it slows down, it slows down, it slows down, it falls down, and it repeats. And you start that cycle over and over automatically. And I'm sorry about that. And I do it because of the shape of the chamber. Most of the competition has always used a cylinder. So they relied on gravity. The higher it went, the gravity eventually slowed it down and it would fall. It makes the chamber very tall. If you look at the Glot from 4 years ago, 5 years ago, or any of the knockoffs here in China, the same size 500-liter machine, the chamber is much taller than a fluid air machine. It has a conical shape. Two advantages, obviously, for processing, the particle slows down automatically. That's fantastic for processing. We talk top spray granulation. This is the best thing in the world. The second advantage is the room. Someone earlier mentioned HVAC in a room. Yesterday we were talking size of machinery. My chamber is shorter. That makes the room ceilings lower. Lower the ceiling, I lower the volume of the room. I lower the volume of the room, I lower the customer's HVAC costs. So from a green initiative, the size of the chamber, height of the chamber immediately helps the customer's green initiatives for HVAC costs. Now again, most pharmaceuticals really don't care about HVAC. They're starting to more and more because they realize that's a big operating cost. But they're still more interested in product. With the product here, the airflow allows me to automatically slow down my material because of the shape of the chamber. This used to be very unique to fluid air, the shape of the chamber. We've used it now since our conception 30-some years ago. We have always got a conical chamber. It's only been the last 4 or 5 years, Glot has started going to a conical chamber. Not quite as much. Their angles are much shallower than ours, but they're starting to go to a conical chamber. They're starting to see the benefits of it. As I said earlier, when your competition starts to copy you, that's flattery. They finally start to realize your design is better than their design. Now, of course, we can't say we're the only one conical, so it's a selling point. There are some conical machines out there that now make sales work a little more challenging. Inside the chamber is a filter bag, or a filter system. The filter system allows the product that's bouncing around in here to stay inside the machine, allowing the air to go out of the machine. Couple of types of filter. The first one, simplest one we do is a one-piece filter bag. This is, does Pfizer have a one-piece filter bag? No, they have blowbacks. One-piece filter bag, just like the name explains, is like a sock. It's a solid sock, open at the top, or filtered at the top, opened at the bottom. It attaches to a ring on the top of the chamber, attaches to a ring on the bottom of the chamber, and allows the product to stay in the machine. These filter bags, which sound very simple in design, have probably 30 years of design on them, because they take a lot of pressure drop. It's not uncommon to have 40, 50 inches of pressure drop across the bag. Think about that, the bag is 10 feet tall, it's 6 feet wide, and you put 50 inches of pressure drop across it. That the tearing forces on the filter bag become very extreme. So getting the filter bags to survive that kind of situation has taken a lot of years of design, failure, repeat. So the filter bags have, I mean, if you look at the revisions, they're probably on 30 to 40 revisions on the filter bags because of the amount of stress and the design work that goes into them. A couple different types of filter bags. We do a larger opening filter bag for coating and a smaller opening for drying because of the size of the particles. Most coated particles are slightly larger. We go to a more coarse bag. Top spray granulation and drying, your powders are very small. We go to a finer material bag. Second one, which is actually Pfizer's machine, is just cartridge filters. So you have a series of cartridge filters at the top of the chamber. Each cartridge is I can back up a little bit. Hold that thought. The filter bag, while running, can be cleaned. So during processing, we can stop the airflow. We leave the fan running because you don't want to stop a big blower continuously. We leave the fan running. There's a cylinder on here. We shake the filter bag to clean it, raise it back up, let the airflow begin. Shaking is kind of like going to the beach and shaking out your towel. As you lower it and snap it back up, it releases material, cleans the product off of it, prevents buildup of too much pressure drop and damage to the bag. The problem with the one-piece filter bag is every time you shake it, you're not processing. So if you shake every 10 minutes, and it takes you a minute to do a shake, so out of every 11 minutes, you only process 10. So you're what, 92% efficient? Maybe not good enough. Second option is cartridges. Cartridges, just like they say they are, they're a pleated cartridge, allow me to get enough surface area. The air goes, product's bouncing around the chamber, goes out the cartridges or through cartridges, product stays in the machine, air leaves the machine. Now cartridges, I don't need to stop processing to clean. I can use high pressure compressed air to pulse the filters clean while running. Kind of like you do in the Model 2 in the process lab. So we pulse the filters while running to get the filters to do this number and release product. Pros and cons of everything. The con of this design is cleaning these filters. Kind of a pain in the butt. The pro is these filters will take more pressure, more vacuum than my fan can create. So my fan cannot destroy these cartridges. If a customer runs, like Pfizer wants to, they want to run 30 days between cleaning. They want to run 24 hours a day for 30 days and then do a cleaning. I'm not sure they can do that, we'll see. But if they were to keep putting powder, fines into the filters to the point where they completely plug them, even if they plug them 100%, my fan at 87 inches cannot damage the filters. The machine won't run, but it can't damage the filters. Whereas on a bag, 40 inches makes me nervous. 45 inches, I really get nervous. You're putting so much force across that bag, it's eventually going to tear open. And when it does, there's no repair. You just throw away a $7,000 filter bag. Buy another one. So, I love filter bags as spare parts. because most customers will buy 2 or 3 of them. So there's a $30,000 spare parts order. Always good for business, but not good for customer. The third one we have is a filter bag and cartridges. So I can use inside the same machine, filter bag and cartridges. Now the advantage of this is I get more surface area. The more surface area I have, the longer the machine can run between cleanings, between pulses, between bag shakes. This is actually the optimal, but the downside is you now have more parts to clean when you do a changeover. So I always tell customers, from a sales standpoint, find out if you can do it with just one filter bag. If you can, it saves a lot of money. If you can't, then you switch to bag and cartridges. What do you think the downfall of cartridges are? What would you consider a con, a negative of cartridges? I'll give you a hint, it has to do with the chamber. In this design, your chamber is product contact. In this design, if you're using a filter bag, your chamber is not product contact, because your chamber is outside the filter bag, which means your chamber is outside the process area. That means a lot less cleaning, swabbing, cleaning validations, etc. It means for cleaning the machine, obviously, it's real simple. The chamber is going to clean easily. You take the filter bag, you wash it, you put it in the washing machine, you're done. The chamber, you hose down it that much just to get dust off of it, it's done. This one, the entire chamber is inside the process area. So I can show you later. I got pictures of Pfizer's machine after 8 or 9 runs. There is product on the walls of the chamber. So what do you do? You got to wash the chamber. The chamber is now product contact. That's a disadvantage of a cartridge-only machine. A couple of pictures of cartridges. So here's the cartridge. Now we're looking now up at the top of the chamber. So you're laying on your back looking at the sky. So here's the cartridges. You can see their plated design. The plates allow me to increase surface area, whereas a cylindrical cartridge has a very small surface area. We can, depending on size of the machine and the customer's requirements for the size of the opening, do stainless steel cartridges as well. I love stainless steel for coating. For a coating application, this, especially a polymer coating, fantastic, because I can take these filters, the mesh slides off, and I can dip them into a low acidic cleaning solution to remove the polymer. Question? Yes, please.
So for the filter bag, the wall of the filter bag is L. Yes.
Is L-proof.
Yeah. So I mean, the air will not go through the wall of the bag.
Oh yeah, the filter bag, absolutely.
Yeah, yeah.
The air will go through the filter bag, but not the product.
So it's only the air goes through the what's that? Cartridge.
Sure. So here's a picture of one right here. So from a cartridge standpoint, the air is going to come up, go through the cartridge. The product's going to stay on this side. The air will go through, up to the top, and out the pipe. On a bag, so here's the bag. The air is going to go through the bag. The product will stay on the inside of the bag, and the air will go through and out the pipe. So the entire bag it's a fabric. It's a fabric. Work for now. It's a fabric bag, so the air can go through the entire bag. So a little demonstration on the filter shake. So standard filter bag, remember, I programmed the intervals in the recipe. 10 minutes, I usually shoot for 10 to 15 minutes, depending on the pressure drop, to shake a filter bag. So when you go to shake the filter bag, the fan goes into a non-airflow position. Usually a valve. You close a valve in front of the fan continues to run. There's no air through the chamber. We shake the filter bag. Normally every 10 to 15 minutes I'm going to do 3 to 5 shakes. The shakes are pretty quick. 3 seconds down, 6 seconds up. The reason I do longer up than down is to ensure it always goes all the way up. So you do a couple of shakes, shake the filter bag, turn the airflow back on by opening the valve, let the airflow come back to set point, continue processing. Simple shaking. Difference between our shakes and our competitors. Obviously everybody copies Glot, so I pick on Glot for most of my examples. Glot fluid bed uses 2 filter bags.
Yeah.
Each filter bag is a series of fingers. What they do is they shake one bag at a time.
Yeah, I know.
They don't stop processing. There is a pro and a con. They don't stop processing when they do filter shakes. Love the idea. Problem is, you have 1,000 SCFM going through 2 filter bags. You close off the air to one filter bag. What happens to the air to the second filter bag?
Increased the air.
You got it. You've increased the air.
Yes.
So you've gone from 1,000 CFM to from 2 bags, so 500 per bag, to 1,000. You close off this one to shake it. So now you've got 1,000 going to 1 bag. Your velocity has just increased by 50%. Your pressure drop has just increased by 50%. So what happens if you look at it through, and Spray's done this a couple times for us using their computational flow lab, what happens is you had both bags, equal powder. There's powder stuck to the bag. You close one to shake it. You took all the powder from this bag and you move it to this bag. And you repeat, and all you've done is move the powder from bag to bag. Our design is get the powder back into the bowl. For drying, it's not that critical because you're going to do a shake at the very end. But for top spray granulation, by stopping the process and shaking and putting the fines back into the bowl, I increase my yields. Depending on the process, somewhere from 3 to 7% higher than a standard Glot yield, because I'm putting the powder that was going like this, I put it back down in the bowl for granulation. So that's the pros and the cons. For granulation and coating, great pro. Drying, really doesn't help much. Between your single filter design and their double. Their double, and I'll show you pictures of it, a little more complicated to assemble. I'm not crazy about it, but that's just me. Cartridges are kind of like a dust collector. We're going to sequentially pulse high pressure air 1 filter at a time. So I'll bang the first one, compressed air. 8 seconds later, bang the next one, and repeat. The pulses are pretty short. They could be ½ second to 1 second pulse of compressed air, stop, and then repeat. The goal is always to pulse each filter every minute. So 8 filters, you set up your pulse for every 8 seconds. If you have both pulse cartridges and filters, what you're going to do is do your pulse continuously. So while you're processing, you're continuously pulsing. And then every 15 or 20 minutes, you're going to stop and shake the bag. Again, the reason for shaking bags and pulsing, twofold. By keeping the particles off the bags, you prevent damage to the filters. More importantly, by keeping the products off the filter bags and keeping it down into the process area, you increase your product yields. Imagine, if you will, you're making a product that's, I pick on Viagra, $17 a pill. Each pill is only 10 milligrams. So if you lose 100 milligrams to your filter bag in every batch, what did it cost you? Now run that 24/7. How much do you save by getting that product back into the yields? It goes back to that return on investment we talked about. I'd rather pay $100,000 more on day 1 and gain $5,000 a day for life. 1 year I've gained back all my money and I start making money. Return on investment. Too many customers look at these processes from a short-sighted purchase. All purchasing cares about, not picking on purchasing cares about how cheap can I buy a piece of equipment. And Thomas and I, Marco, Frank, Tony, we go out and talk to these customers, and their concern is, I want the cheapest machine I can buy. That's all they care about, the bottom line. What we need to do is convince them and show them that the $100,000 more up front is worth it, because you're gonna make them more product and save them more utilities per day, per batch. 5,000 a day, 300 days a year is 150 grand a year. 20 years on a machine is 30 million? Pfizer's been running 20 years on the same machine. So the 5 grand a day I saved them, or made them, what was that made over the course of 20 years? And that's what we need to show them, because we are not, I'm gonna tell you right now, we are not the cheapest, Thomas can say this, we are not the cheapest manufacturer out there. A lot of things we can do to become cheaper. The localization process will help save money. Removing design features that this market doesn't want. There's things we can do to lower our costs. But guys like our friends in Germany are manufacturing in India and then shipping it to Germany. An Indian manufactured product's pretty cheap. That's gonna be a tough one to beat. So we've got to be the solid customer on the return on investment. Goes back to we sell them on our skills, our intellectual property, and then we sell them on our return on investment. So we talked about the air handler, the plenum, the bowl, the chamber filters. Let's look at the outlet of the machine. So from the outlet pipe all the way to the fan. On a standard machine, we're going to have an outlet temperature probe. We're going to have potentially block valves on the inlet and the outlet. The block valves are there for a couple purposes. It makes the filter shakes more efficient because you remove any airflow going through the chamber. But more importantly, the block valves on the inlet and the outlet allow me to seal off the chamber but not running. Why is that important? Most process rooms are positive pressure. If you have a positive pressure in the room and somebody opens a can of dust product, it's going to end up going into the piping. It goes into the outlet piping, maybe not so bad because it's on the outlet of the product. If it goes into the inlet piping, the next time you turn the machine on, you just suck that product right into your machine. You've just contaminated a batch of product. And if one's a Ritalin or a anti-anxiety drug and the other one's an amphetamine, that's a bad combination. The outlet can be dangerous too. India, Force Labs, Allergan, who bought Force Labs, recently had an issue with a fluid bed that had product in the outlet pipe. It had gotten so bad that at one point chunks of product came out of the outlet pipe and ended up in the chamber. That was a bad one. When you open up the machine and you're expecting to find white product and you find globs of red product. So nowadays we offer as an option valving for both the inlet and the exhaust. We call it isolation valving to ensure that the machine's not in use, we're not getting a chimney effect. We're not getting powder from the room migrating into the piping and risking contamination of the next product. That's another one from a sales standpoint. We start talking to customers and looking over PIDs. Here's our PID, here's our drawing. Is your competition providing these valves? No. Great, we can remove them, but more importantly, we can turn to the customer and say, well, you realize by not providing that valving, they're not protecting you from cross-contamination. Those valves, which call it $5,000, easy numbers, is protecting per valve, so 10 grand. Having those valves is protecting them from cross-contamination. Cross-contamination results in recall of material. People die from cross-contamination. So right away you tell the customer, well look, Mike, your competition's not doing this. My standard is to do this and here's why. You again look like the expert, more knowledgeable than your competition. The customer may still ask you to remove the valves because he's cheap, but at least now you present yourself as, yes, I'm more expensive and here's why. Also on the exhaust, there's an outlet filter housing. That outlet filter housing could be a HEPA filter. It can be a torrent dust collector, depending on customers' requirements. The reason for it is that any powder that gets past the filter bags, we want to stop before it gets to the fan, and we want to stop before it gets to the environment. Really the same whether it's a bypass or a non-bypass machine. You still have outlet temperature. You still have lock valves, outlet filter housings, the fan. I show an airflow valve here, obviously. Airflow valves are on the older machines. The newer machines are using VFDs that we talked about earlier. So here's a couple examples of the outlet filtration system. The picture on the left is a HEPA housing. That one looks like it's got 2 filters in it, so that's probably a 4,000 CFM unit. And all it is a static filter. When the filters become dirty, the gauge trips, sends an alarm to the machine, maintenance goes up, pulls the filters out, and replaces them. The con of these filters is that they're replaceable, not cleanable. HEPA filters can't be cleaned. So when that pressure drop exceeds manufacturer's recommendation, you throw away 2 filters and put 2 more in. Now, I can only do that once every couple of years. It's not a big deal. If you're losing a lot of product through your filter bag, either because of process, because of assembly, because of operations, you start going through these once a month, we're talking a lot of money. In a coating operation, you plan on dust leaving the fluid bed. If you're coating a bead and the bead breaks, you don't want the bead to stay in the chamber. You want it to leave the chamber, so you use a bigger bag. If you're losing product, you don't want to lose it to this because you could create too much pressure drop too quickly and spend too much money on filters. Then you switch to a dust collector. The dust collector basically is a series of cartridges. Air goes through them, product stays out, falls into a collection drum, air leaves the filter cartridges. I think you got Donaldson dust collectors back here in the manufacturing area.
Dust collector.
I thought I'd seen them, I don't remember now. I thought I'd seen dust collectors back here. But those are the 2 types of dust collection systems on the outlet of the machine. Static HEPA filters or a Torrent Donaldson dust collector.
电友是不是给我们看过这个？就是粉尘收集这个。
但是设备里面的其他的粉质是不是？
不是我们，是吗？
Go ahead.
He asked me if it is all the Johnson dust collection system in Pfizer.
No, Pfizer, surprisingly enough, Pfizer went with HEPA filters on the outlet. I was a little shocked by that because they complained on the 500 of product leakage from the machine. Now we've now run about 25 batches of material through their machine. We've just recently opened up the outlet filters, the housing, and kind of did a, the white glove test, and really didn't find a lot of dust up there at all. So they may have made the right choice. And again, it comes down to returns. The HEPA housing is very cheap to buy. If you go through filters once every year, cheap to maintain. Go through filters every month, very expensive to maintain. The dust collector, much more expensive to buy. But your operational costs are very minimal because the way they work, you don't replace the filters. So it's a trade-off.
Oh.
That's a tough one to decide which one you buy, which one you don't. Normally what we look at it, if you're doing a standard drying operation, standard top spray granulation operation, we try to push towards the HEPA housings.
Okay.
If you're doing a coating operation, or you're planning on doing coating operations, we tend to push towards the dust collector. Because in standard coating operations, and we'll talk about this a little later, standard coating operations, you want the product to leave the chamber. You don't want bad product to stay in the chamber.
Yeah.
So where's it gotta go? It's gotta go to the outlet. And if you're doing a coating and you're putting it on your outlet filters, you're in trouble. So we tend to look at it that way. Drying is a HEPA, coating is a dust collector.
So I have the question.
Yes, sir, please.
Yeah, if you are using the dust collection, then the HEPA filter, is it required?
No.
Either any one. Yeah.
Technically by law,
How is it
this does not have to be a HEPA.
static?
This can be a standard 85% filter. According to, well, I say according to law, according to governments, most governments will let you use an 85% filter there. So you lose a little bit of fine powder. That's okay. We try to push customers to HEPA again to protect the environment on the outlet. Some customers decide to save money.
I
Yes.
have a question about the dust collect system. Is this system need a blower themselves?
Some do, some don't, depending on how much pressure we're talking about. Some of them will use the fan, my fan, to suck the air through them. Some of them, like coating pans, coating pan blowers don't have a lot of head, so they'll use a secondary blower on the dust collector. Ours normally will not, because when we size our fan, we will size the fan with enough head, enough suction, to handle the dust collector. Good question.
Thank you.
We talk about things on the blower, the outlet blower. Now this is a small one, it's only a 150 horsepower unit. The blowers are relatively stupid devices. The air comes in the center, it's a big paddle wheel rotating, it takes the air from the center, sucks it and forces it out the edges and out of the fan. Really a simple device. However, an extremely dangerous device. Pfizer Plant 1 had one grenade blow up 20 years ago. They mounted it on a vibration system unapproved by us, and what happened is it vibrated so bad that the entire housing separated. The motor came off the base. Parts flew out of the building. That's how bad it was. Give somebody how bad it was. The motor on their machine rotates at one speed, 3,600 RPM. It threw a chunk of metal that was 150 pounds, 70, a 65 kilo piece of metal left the building
It's dangerous.
from the third floor. Luckily it landed and didn't hit anyone. It could have killed quite a few people. Back in the old days, we provided fans with an option. It was on the option list that Thomas would present to someone, called a vibration sensor. And of course the customer would say, no, I've got good maintenance, we're gonna check the bearings every week, not an issue, we'll take care of the maintenance, don't charge me the $15,000, whatever it was. We'll take care of it ourselves. That was Pfizer's option. Pfizer chose not to buy the vibration switch. When that fan came apart, one, as it started coming apart, the vibration switch should have given a warning. Two, before it came apart, the vibration switch should have stopped the machine. It didn't, because they didn't want the switch. So it vibrated so bad, it completely came apart. We now require and provide on any fan, minus the portables. The portables are different fans, or regeneratives. Any paddle wheel style blower, turbo blower, we are going to provide a vibration switch. It's actually an electronic sensor. It's going to measure, it's an accelerometer. So it's going to measure the vibration at the fan in real time. If that vibration level exceeds safe limit 1, you get a warning downstairs in the fluid bed. You exceed safe limit 2, it stops the fluid bed. You cannot run. That switch has saved me from multiple catastrophic failures in the last 20 years. Not an option, we provide it. But it's another great one to talk to your customers about. When you're talking competition, is your competition providing the safety? Why aren't they? These fans do come apart, and when they do, people get killed. We were very fortunate when Pfizer 1 came apart and no one got killed. So, vibration switch, mandatory. This one actually shows, here's the valve on the outlet. This is an older machine relying on the valve to actually control the airflow, and new ones use VFDs. This is probably when we're talking about things that are difficult to spec. The dust collector is easy. Engineering will give you a spec. You contact Donaldson or Torrit, whomever, and you find what meets the spec and you buy it. Those are easy. The small blowers, regenerative blowers, those are easy. These are the ones that are more difficult. Finding a vendor who can tell you it's going to run 5,000 CFM at 80 inches. They all provide theoretical fan curves. And the theoretical fan curves are usually crap. So finding someone who's got a true fan curve that they're willing to guarantee is worth their weight in gold. Because a lot of them will give you a theoretical, and then in the small print, tell you the curve it can be off by 10% based on temperature compensation, off by 10% just because. So you can have a 20% error on the curve. Wow, 20% in pharmaceuticals is a pretty big number. Which is why when we find manufacturers of these fans we trust, we usually stay with them. Fan curves. We talked briefly about if you add pressure drop to a chamber, your filter cartridges, your filter bag, etc. become dirty, you increase the pressure drop. If your fan doesn't have enough head, as the pressure drop increases, what's going to happen? So let's just say we have a fan operating right here at 4,000 CFM. And we increase the pressure drop, so our static pressure goes up. What's happening to our airflow? Our airflow is decreasing. You can actually have a system with so much pressure drop in it because of dust collector. Your question regarding dust collectors and fans. If your dust collector doesn't have enough, if your dust collector creates too much pressure drop, because the vendor told you it was only create 10 inches, it actually created 20 inches. And you start blinding off your filter bags, you can run out of airflow. Either because you don't have enough horsepower or because the pressure drops increased. So this is where, when it comes time to start speccing out blowers, we'll start looking at your vendor's fan curves very closely. This used to be a big problem. You would run out of blower and not be able to reach the airflow you caught. Your URS or your DQ says we will give you a blower good for 11,000 meters cubed per hour. The customer may not need it ever, but if you put it in that URS or your DQ and he wants to be difficult, he can say, look, I bought something good for 11,000, you can only do 10,000 because your torque dust collector is wrong. Fix it. They don't care who pays for it, you're going to pay for it. So fan curves become very critical. Finding a manufacturer whose fan curve matches the actual fan. It's why the smaller machines up through 50 liter, we use regenerative blowers. They make thousands of them per year. They're not custom. So their fan curves are actual, not theoreticals. The big ones like Pfizer, when you start talking, this is like 150 horsepower or 250 horsepower, they're theoretical fan curves. So we usually actually upsize them at that point to make sure that the vendor is, that we don't, make sure we have enough horsepower. Make sure we have enough airflow. Also on the machine, one of the systems we haven't talked about, both inlet and outlet, is explosion protection or explosion isolation. Now I keep using the word explosion, remember, we try to make the customer feel comfortable, we call it deflagration. But what happens inside a chamber, again, you got powder moving around, potentially solvent powder. You have air, oxygen coming through the system at 11,000 meters cubed per hour. So you're feeding it all the oxygen it needs to start a fire. You have the fuel source, the product. All you need is a spark, ignition. Heat or spark is ignition. If you get ignition inside of a fluid bed, some of them can be quite violent. Abbott Labs has had quite a few of them. When it happens, you have to protect things. New US codes require every fluid bed, no matter what size, let's take it back, no matter what product it's running, to have either isolation, venting, or suppression. One or all must be required. That's kind of a new one now. The original Pfizer machine has no protection on it because it wasn't required when that was built. The new US codes require it. The Chinese codes, we keep hearing different things on. Janssen & Janssen told us there was no code. Pfizer said differently. So it's kind of a gray area. Be interesting to research long term to find out what the Chinese code is. But on our machines now, we assume everything's being built to our standards based on US code. So we may be overbuilding them, but we're basing it on US code. And that is every machine has to have either suppression or isolation. Isolation is what you see here. This is a valve. There's a cylinder, a pneumatic cylinder on the top. This little ball here is a 350 psi tank of nitrogen. If the chamber goes positive, this sensor sees it. This sensor sees either a high positive pressure or a very quickly changing pressure. We're talking 35 millibars in 30 milliseconds. If it sees that, it senses that as an explosion, a deflagration. Faster than the shock wave. Now remember, explosions moving at the speed of sound. Faster than the speed of sound can travel from the chamber through the piping. This controller will send the signal to that valve. That valve will release 350 psi. This is the gate valve. That valve will slam straight down, sealing off the explosion, preventing it from going someplace we don't want it. In this case, I don't want it going to the fan. That shock wave hits the fan, that fan will just explode, someone could die. On the inlet, it's the air handler. That air handler is not designed for explosions. People could die. Give you some idea how fast this works. Like I said, it's faster than the speed of sound. These valves close with so much force that this bottom half here is a solid block of rubber. When this valve slams into it, it'll actually go through the rubber. That's how fast and how hard it's closing. When these valves close, I can't reopen them. I'm not allowed legally to reopen them. The manufacturer, Fenwal, which is a local manufacturer here in Shanghai, has to come on site, open the valves, reset the initiating circuits, reset the control board to put the machine back in service. More importantly, EHS, Environmental Health and Safety, from whatever company you are, is going to ask what happened. The investigation will shut down production. That's a containment system. Fenwal also does a suppression system, which is what Pfizer opted for. So Pfizer has 6 or 8 sodium bicarbonate tanks on the machine. If they see a deflagration, same sensor, it'll send a signal to the tanks. The tanks will open up and blanket the area of sodium bicarbonate, putting out the explosion. Same thing happens. Once it occurs, the machine's not running. Fenwal has to come on site, reset every tank, rebuild the systems, start the investigation. And oh, by the way, Pfizer now has to clean the machine. It's now been filled with sodium bicarbonate. The cost of these, I say this, the cost of either one of these events, whether it's the valves or the tanks, is measured in tens of thousands of dollars. We will have a deflagration within the next 18 months at Pfizer. I'll guarantee it. But theirs won't be an actual explosion. Theirs will be the fact that all of their wiring, none of their wiring is in conduit. So it's all laid open on top of the machine. These systems are fail-safe. If the board, the control board, sees a wire open circuit, it's going to assume something's gone wrong. And it's going to do what it can to make the machine safe. Fail-safe means it's going to close the valves or detonate the tanks. So I've said it now to everybody here, so when this happens, when the customer calls and says this Fenwal system just went off, I've now said it to everyone that it's going to happen. And it'll be Pfizer's responsibility. These control systems, and again, the control system's not part of my system. I don't build the control board. A separate company builds it. They're responsible for it. We can train people to do PMs on them, but my spraying systems won't let our people take the liability for someone dying. So Fenwal's got to come on site every 6 months to a year and do the PM on the system themselves. Questions on the hardware? Air handlers, fans, inlet valving, outlet valving, filter cartridges, outlet filtration, fans, dust collection, explosion protection.
Sorry.
Please go ahead,
Yeah.
ask, don't worry about it, go ahead.
The substance in the chamber, I mean the carbon, or carbonate dioxide.
Hydrocarbon.
The substance in the
Suppression.
suppression
Oh,
chamber.
suppression system, yeah, sodium bicarbonate.
Carbonate.
Yeah,
Carbonate.
sodium. It's a
Oh, yeah, I know. Yeah.
the same thing they use. It's like halon, only halon is not food grade. Sodium bicarbonate is food grade, so it's easier to clean in pharmaceuticals.
Okay.
But it basically blankets it with this dust, this
Mhm.
powder. The powder basically, for lack of a better word, displaces the oxygen,
Mhm.
and that puts out the explosion.
Okay. Thank you.
You'll see,
Huh.
in fact, I'll show you. You'll see at Pfizer. Can I get lucky? Let's find a picture of it. There you go. So on the Pfizer machine, these red tanks
Mhm.
are sodium bicarbonate. So there's one on the inlet pipe, one on the outlet pipe, one on the inlet to the chamber, two on top of the chamber, one on the charge pipe. They all go off together. So if the one sensor sees a failure, all 6 tanks are going to go off at once. And it's probably a 3-day, 4-day repair, plus the cost of downtime, plus the cost of the cleaning, plus the cost of the throwaway batch. So when I say measured in tens of thousands of dollars, it is. We always hope that when you see one, it's happened for a real reason. 26 years, I've only had 3 real reasons for these deflagration systems to go off. I probably had 20 of them go off. Most of them fail because of operator or customer neglect. The big one is they remove a wire. Bad situation. The other one is a customer takes his guys are troubleshooting something else. They don't think what they're doing, and they take their multimeter and they troubleshoot a terminal block. That 9-volt battery is more than enough to trigger the system, and it activates the valve.
Yes.
So that's 70+%, that's more than that, 3 out of 20. So that's 85% of my systems that fail are because of operator neglect or customer neglect. I've had 3 real deflagrations. One was a slow-moving explosion. So slow-moving, it ends up being the DPDT, or fast-moving but low pressure. So the DPDT sensor went off and triggered it. The neat thing about this is the Fenwal system allows me to plug in a computer after an event and look at what happened at millisecond intervals for the last 5 minutes to see what happened. Which is nice. At least you know right away what is real or mechanical. We have had mechanicals set this off. We had a system operating under high vacuum. The torrent dust collector was actually running over 50 inches of negative. The chamber was running another 20+ inches. They stroked the valve, which turned the dust collector off. So the system went from -70 inches to -20 almost immediately. That's actually a positive rate of change. That positive rate of change triggered the system and set off the devices. But again, the data logs from the Fenwal system gave us enough information we could troubleshoot. When this occurs at Pfizer, it's be a messy phone call, and Thomas and I will be going to Suzhou to explain to them why. And the reason I say it's going to happen, let me show you a picture of why. Oh, come on. I take pictures of everything and I can't find one. That's too bad. I don't see what's up out. The top of the chamber. Oh, here we go. Can you zoom in on this one? There we go. The top of the chamber. Every wire going to each one of these tanks, they put an inside conduit to within 3 feet of the tank. The last 3 feet is just a cable hanging there. So when the maintenance guy steps on it and pulls it out, he's going to activate the system. And we've told this to Li Feng in writing. We've told it to him in meetings. We've told it to them every chance we get. That's probably the only place I got a picture of it, that they're going to grenade the system. And it's gonna be a couple probably $20,000 in damages. So it's noon now. Hopefully I don't have another meeting. So let's plan on meeting back here. What time do you guys usually take lunch till? 1 or 1:30? What time do you
Maybe no.
What's that?